In the black silence of the early universe, long before galaxies like our Milky Way spun their grand spirals across the cosmic canvas, something flickered into existence, a ghostly glow from a time nearly lost to the darkness of creation. That ghost was Himiko. A name taken from a mysterious shaman queen of ancient Japan, yet now shared with one of the most enigmatic objects in the observable cosmos. Himiko is not just a galaxy, it is a message, a defiance, a riddle radiating from the edge of time. But before we continue, subscribe to the channel and like the video. Roughly 800 million years after the Big Bang, the universe was still in its infancy, barely 6% of its current age. The cosmos was undergoing profound transformation. It was the Epoch of Reionization, when light was beginning to break through the fog of neutral hydrogen that blanketed everything. This was a time when stars had only just begun to burn, and galaxies, if they formed at all, were thought to be small, chaotic, and dim. But Himiko shattered that expectation. It was massive. It was bright. It was organized. It was, in every way, something that shouldn't be there. Himiko appears not as a structured spiral or an elegant elliptical galaxy, but as a hazy, sprawling beacon of energy, nearly 55,000 light-years across. That's about half the size of our Milky Way, a shocking statistic considering that most galaxies at that era were puny, more like cosmic building blocks than completed structures. Its sheer size alone makes Himiko a cosmic anomaly. But its story doesn't end there. Its light, traveling for nearly 13 billion years, brings with it secrets of a universe just beginning to awaken. A universe transitioning from the darkness of ignorance to the illumination of structure, energy, and complexity. To call Himiko a ghost is not poetic exaggeration. What we see is not what is, but what was. When astronomers gaze at Himiko, they are not seeing the galaxy as it exists today. In fact, they are not seeing it even as it was in recent galactic terms. They are witnessing its ancient light, fossil radiation that escaped the gravitational pull of this distant system billions of years ago, crossing the ever-expanding void of space, finally reaching us as a snapshot from a forgotten chapter of cosmic history. But why is Himiko important? Why has it captured the imagination of scientists and cosmologists alike? Because it doesn't fit. It stands out like a lighthouse in a landscape of candle flames. The early universe should have been too chaotic, too young, and too disordered to support such a luminous and massive system. And yet, Himiko defies the models. It is as though we have stumbled upon a skyscraper in a village where we expected only huts, built too soon, too fast, and by unknown hands. In a way, Himiko challenges not just scientific theory, but our philosophical grasp of time and creation. It reminds us that the universe is still full of surprises, that the cosmic story is not as linear as we once believed. Himiko is not just light from long ago, it is a message from the universe's earliest architects, whispered across eons. You do not know everything. And so, we begin with a ghost. A ghost that glows with secrets. A ghost from the cosmic dawn, breaking through the silence of time, daring us to understand the impossible. It wasn't discovered in the way most galaxies are, through bright clusters and familiar constellations or in routine observational sweeps. Himiko emerged not with fanfare, but as a whisper caught in the faint signals of deep space surveys, whispers that only the most sensitive instruments could detect. Astronomers, scanning the heavens with powerful infrared telescopes, were looking for the earliest possible signs of galactic structure. They weren't expecting something so immense. The data came from the Subaru telescope on Mauna Kea in Hawaii, an observatory that specializes in capturing high-resolution images of the distant universe. Paired with the Spitzer Space Telescope and later confirmed with the Hubble Space Telescope, these instruments looked deeper and farther than any human eye could ever hope to see. And in that abyss of time and space, they found a strange, luminous smear, diffuse but prominent. It wasn't a star. It wasn't a typical galaxy. It was something else. Something big. The light was so stretched by cosmic expansion that only infrared sensors could pick it up. Visible light emitted from Himiko had been redshifted by the expansion of the universe to longer wavelengths, invisible to the naked eye. What this meant was profound. they were seeing light that had traveled more than 12.9 billion years to get here. A direct glimpse into the past. A photographic fossil. Astronomers didn't immediately know what they were looking at. The object was unusually bright, far larger than expected, and the distribution of its light was diffuse, not neatly centralized. Follow-up observations were necessary, and more instruments were brought to bear. Himiko slowly began to reveal its secrets under the scrutiny of Spitzer's infrared lens and Hubble's deep-field precision. This wasn't just a happy accident. It was the result of a broader quest, a deliberate search to identify galaxies from the earliest epoch of the universe's formation. These deep surveys are like archaeological digs into the fabric of space-time, each faint signal a possible artifact. But even among these carefully selected signals, Himiko stood out. Not just for its brightness, but for its implications. It was too big, too bright, too early. And so, in a field of faint smudges, where most early galaxies are tiny and faint, Himiko burned like a beacon. It became a point of focus for astronomers trying to push the boundaries of what we know about the universe's formative years. Every wavelength collected, every signal confirmed brought us one step closer to understanding this mysterious colossus from the ancient sky. What made its discovery especially exciting was not just the object itself, but the way it was found, an act of looking backward, not just through distance, but through time. When we observe galaxies like Himiko, we are not observing them as they are, but as they once were. The light reaching us now began its journey when the first complex molecules were just forming. Before Earth. Before the Sun. Before most of the elements that make up our own bodies even existed. The discovery wasn't just a scientific event, it was an existential moment. A reminder that the universe holds onto its secrets tightly, revealing them only to those who learn to look far, deep, and long. And Himiko, buried in the cosmic past, had waited nearly 13 billion years to be seen. When we look at Himiko, we aren't seeing it as it is, we're seeing it as it was, nearly 13 billion years ago. That light, now just reaching Earth, began its journey only about 800 million years after the Big Bang. The universe at that time was a radically different place. It was young, dense, and in the middle of one of its most transformative eras. Himiko's light is not just old, it's ancient, a direct relic from when the cosmos was just 6% of its current age. This is one of the strangest truths about astronomy. The farther we look into space, the further back in time we're actually seeing. Light doesn't travel instantaneously. Even at 299,792 kilometers per second, it still takes time to cross the immense chasms of the universe. So when Himiko's photons hit our detectors, they're carrying a record of the universe's conditions from an epoch long vanished. At just 800 million years old, the cosmos was in its cosmic toddlerhood. It had barely begun building the large-scale structures we now see dominating the modern universe. Giant galaxy clusters, swirling spiral arms, and mature elliptical galaxies didn't exist yet. The earliest stars, massive, short-lived beacons made of pristine hydrogen and helium, had begun to flicker into existence, triggering the universe's shift from a cold, dark fog into one that glowed with light and structure. But here's where the mystery deepens. The universe at that time was still filled with neutral hydrogen gas, which absorbed and scattered light. Galaxies trying to shine through this fog had their light muffled, making it incredibly hard for astronomers today to detect them. Yet Himiko shone brightly enough to be seen from this era. Somehow, this galaxy was blazing with enough intensity to punch through the cosmic haze and send its message across the eons. Its discovery confirmed that galaxies had not only started forming earlier than many models predicted but were already growing to enormous sizes in very short timescales. This wasn't just an early galaxy, it was a full-blown, large, complex system sending a powerful signal through space and time. And that signal had been in motion for nearly the entire history of the universe before it ever touched one of our telescopes. What's even more profound is how stable that light remained. Through the cosmic expansion, countless gravitational interactions, and all the noise of the universe, those ancient photons survived intact, uncorrupted, pure, and meaningful. They carried the fingerprint of Himiko's original energy output, encoded in the subtle variations of wavelength, intensity, and spectrum. When astronomers talk about cosmic archaeology, this is what they mean. Himiko's light is a preserved relic, a time capsule from a universe that no longer exists in that form. It gives us a real, observational glimpse into the conditions, physics, and mysteries of the early cosmos. And perhaps the most humbling part is this: the Himiko we observe is long gone. Whatever that galaxy is today, if it even still exists in its original form, is unknowable to us. The light we see is a fossil. The real, present-day Himiko might have merged, evolved, or been consumed by something larger. But what we do see is a snapshot, frozen in time, of a galaxy shining just 800 million years after time itself began. That light didn't just travel across distance. It traveled across every epoch of universal change. Past the formation of the first heady elements. Past the birth of our sun, past the assembly of the earth. Past the rise of humanity. Past everything we know. And it reminds us that when we peer into the deep sky, we are staring through layers of time far older than anything we can imagine. In the early universe, galaxies were expected to be small, chaotic, and still assembling themselves from the primordial soup of hydrogen and helium. Think of them as seedlings, little patches of star formation scattered across the vast, cooling cosmos. They were messy, fragmented, often low in mass and lacking the majestic structure we associate with modern galaxies. This is what the prevailing models of galaxy formation predicted. And for the most part, these models held up, until Himiko appeared. Himiko shattered those assumptions with sheer scale. Spanning approximately 55,000 light-years across, it rivals the diameter of the Milky Way, which took billions of years to reach its current size. The Milky Way, a massive spiral galaxy with hundreds of billions of stars, didn't reach its present form until far later in cosmic history. Himiko, however, seems to have formed a galactic structure of similar magnitude in a tiny fraction of that time, just 800 million years after the Big Bang. That kind of growth simply shouldn't have happened so fast. For a galaxy to reach such a scale so early, it would need a staggering amount of matter, both visible and dark, condensing and collapsing under gravity with incredible efficiency. In standard cosmological models, it takes time for dark matter to clump together into gravitational wells deep enough to attract large volumes of baryonic, normal, matter. It takes more time still for that matter to cool, condense, and ignite into stars. And yet, Himiko seems to have accelerated this entire process on an almost impossible timescale. The size estimate of 55,000 light-years across is not a speculative number. It's based on careful observations of the diffuse Lyman-alpha glow emitted from the galaxy. This glow traces the spatial extent of ionized hydrogen gas, which outlines the rough boundary of the galaxy's reach. Instead of being a tightly wound spiral or a bulging elliptical, Himiko appears as a vast, elongated cloud of brightness with 3 bright knots embedded inside, each one possibly a massive star-forming region or an independent proto-galaxy in the midst of merging. This alone is rare. Most galaxies discovered at high redshifts are compact, sometimes just a few thousand light-years across. Even when astronomers locate bright galaxies from the early universe, they're typically small in comparison to modern galaxies. Himiko is an outlier, occupying a place in the data that sits far beyond the expected limits of galactic size for its time period. But this isn't just about spatial measurements, it's also about mass. The estimated stellar mass of Himiko is immense, with models suggesting a range of tens of billions of solar masses. That puts it well beyond the typical mass range of other early galaxies and suggests that a tremendous amount of star formation must have occurred in a very short time. While most early galaxies were just beginning their assembly, Himiko had already built a massive infrastructure: stars, gas clouds, and gravitational cohesion. How could such a massive structure form in a universe so young? Theories abound, but few provide satisfying answers. One possibility is that Himiko formed in a region of the early universe where dark matter was unusually dense, allowing rapid structure formation. These regions, known as overdensities, would act like gravitational traps, accelerating the collapse of gas into stars and enabling faster galactic evolution. If Himiko resided in such a special environment, it could explain part of its anomalous size. Another idea is that Himiko isn't a single galaxy at all, but a triple merger, a convergence of three massive proto-galaxies in the process of coalescing. This interpretation aligns with the three bright clumps visible in Himiko's core. If these clumps are independently forming stars at high rates, and if they're gravitationally bound, then Himiko might be a snapshot of a major galactic merger in progress. Mergers are known to drive rapid star formation and can lead to the rapid buildup of galactic mass. Even so, the scale remains daunting. For a galaxy merger to be happening just 800 million years after the Big Bang means that all three of those proto-galaxies must have already formed, grown to considerable size, and fallen toward each other through gravitational attraction, all in a cosmic blink of an eye. Then there's the question of feedback. Star formation at such rates typically produces large amounts of radiation, stellar winds, and supernova explosions, all of which can disrupt surrounding gas and slow down further star formation. Yet Himiko seems to be overcoming this natural braking system. It continues to shine brightly, undeterred by the forces that should be blowing its material apart. Its structure also hints at a more stable system than what astronomers usually expect from high-redshift galaxies. Instead of a chaotic clump of gas, Himiko appears to have large-scale organization. Even though it doesn't show signs of spiral arms or a well-defined disk, its enormous reach and concentrated bright regions suggest a degree of internal structure, something unexpected at such an early time. The very presence of such a galaxy forces us to rethink the timeline of galactic maturity. If galaxies like Himiko can exist so early, then galaxy formation models may be missing key ingredients. Perhaps star formation is more efficient in certain early conditions than previously believed. Perhaps the distribution of dark matter in the early universe was more varied than we think. Or perhaps there are feedback loops and formation mechanisms we've yet to fully understand, processes that allow for rapid growth under the right cosmic conditions. What's also fascinating is what Himiko tells us about its cosmic neighborhood. Large galaxies don't exist in isolation. Their presence typically signals that other structures, such as smaller galaxies, gas filaments, and dark matter concentrations, are nearby. Himiko might have been part of a protocluster, an early assembly of galaxies that would one day form a larger galactic system. But at the time of observation, Himiko seems relatively isolated, further deepening the mystery of how it acquired so much mass and structure without the influence of a bustling local environment. Its very name, Himiko, evokes mystery and power. In Japanese history, Queen Himiko was a distant, possibly mythical ruler shrouded in legend and silence. The galaxy named after her reflects a similar aura, powerful, elusive, and challenging our knowledge of what should be possible. At 55,000 light-years across, it sits at the intersection of discovery and defiance, a giant among the newborns of the cosmos, illuminating a path into the earliest epochs of galactic history. And in doing so, Himiko leaves us not with answers, but with questions. How many others like it might still be hidden in the darkness? Was Himiko unique, or merely the first of its kind that we've seen? If the early universe could birth giants, then perhaps our view of the infant cosmos has been far too narrow. When astronomers first pieced together the structure, brightness, and immense size of Himiko, the initial reaction was not excitement, it was disbelief. The discovery didn't just raise eyebrows, it rattled the foundations of long-standing cosmological models. For decades, our understanding of how galaxies form and grow has rested on a timeline, one that suggests gradual build-up from small structures into larger ones, a slow accretion of mass over billions of years. Himiko, by contrast, seemed to leap ahead of schedule, as if skipping several key evolutionary steps in the process of becoming a massive, luminous galaxy. This was never supposed to happen so early. According to the lambda cold dark matter model, the prevailing framework that describes the large-scale structure of the universe, galaxies form hierarchically. Tiny fluctuations in the density of dark matter collapsed under gravity shortly after the Big Bang, forming small dark matter halos. Gas then collected in these halos, cooled, and formed stars, eventually merging with other halos to create progressively larger systems. This process, known as hierarchical merging, takes time, a lot of time. Massive galaxies like the Milky Way were supposed to take billions of years to grow. And yet, Himiko was already enormous when the universe was less than 1 billion years old. What this suggests is either our models are incomplete, or Himiko represents a rare exception that exists in defiance of our expectations. And if there's one thing astronomers have learned over the past few decades, it's that exceptions have a habit of rewriting the rules. The surprise wasn't limited to size alone. Himiko's brightness, especially its powerful emission of Lyman-alpha radiation, indicated a furious rate of star formation. Galaxies from this early era were expected to be dim, forming stars slowly and inefficiently, limited by the lack of metals and complex cooling agents in their gas. But Himiko was blazing, producing new stars at a rate of potentially 100 solar masses per year, comparable to or even exceeding modern starburst galaxies. Such a high rate of star formation should also create feedback effects, powerful radiation, winds from massive stars, and supernova explosions that disrupt further star formation. Himiko, somehow, seemed to be resisting or overcoming these self-regulating mechanisms. For context, galaxies from that epoch, about redshift C6.6, are typically small and difficult to detect. Their Lyman-alpha emission, a signature of young, hot stars ionizing hydrogen gas, is often faint or scattered due to the thick fog of neutral hydrogen still permeating the universe. Himiko's light, however, cut through that veil with surprising clarity. It wasn't just visible, it was dominant. That level of luminosity in such a young system didn't fit the models, especially not in a galaxy that appeared relatively dust-free and lacked signs of an active galactic nucleus. To appreciate just how disruptive this discovery was, consider that Himiko forced cosmologists to revisit the efficiency of star formation in the early universe. If gas could cool and collapse faster than predicted, perhaps due to early local overdensities, or interactions with dark matter halos more massive than expected, then perhaps the cosmic speed limit for galaxy formation needed revision. Some theorists propose that Himiko might reside in a rare, high-density region of space that collapsed rapidly into a massive halo, accelerating its development. Others speculated that early feedback mechanisms, like supernova-driven winds, might not have been as effective in slowing star formation as previously believed. There was also the question of metallicity. Early galaxies formed from pristine hydrogen and helium left over from the Big Bang. Without heavier elements, those forged in the hearts of stars, gas clouds struggled to cool efficiently. This should have limited early star formation rates. But Himiko defied that, suggesting either rapid early enrichment by massive first-generation stars or an unknown mechanism allowing efficient cooling even in low metallicity environments. Himiko didn't just challenge our understanding of galaxy formation. It challenged our confidence in how we interpret the data we gather from the early universe. If one Himiko exists, could there be others? How many early massive galaxies are lurking just beyond the limits of our current detection capabilities? And if they're common, why haven't more been seen? These are the kinds of questions that keep cosmologists awake at night, because the implications stretch far beyond a single galaxy. The reaction from the astronomical community was one of both awe and caution. Himiko might be an extraordinary case, a statistical outlier, a cosmic fluke. But even flukes have meaning. Even one counterexample can expose a crack in the foundation. Scientists began re-evaluating assumptions, refining simulations, and preparing to look deeper with upcoming instruments like the James Webb Space Telescope. Because if Himiko was a sign of more to come, our entire picture of the early universe might need to be redrawn. The irony is striking. Himiko, a name inspired by an ancient queen shrouded in mystery, now finds itself as a queen in the early cosmos, a symbol of something vast and unknowable, reigning over a part of the universe we thought we understood. Its surprise presence in the cosmic timeline is not just an anomaly, it's a message. A reminder that the early universe may have been more chaotic, more efficient, and far more creative than we ever imagined. As scientists continued to study Himiko, it quickly became clear that this was more than just a large galaxy. It was a cosmic disruptor. It had arrived unannounced, unexplainable, and undeniably brilliant. It wasn't just surprising. It was paradigm-breaking. In the vast, early darkness of the cosmos, when neutral hydrogen still smothered the light of most newborn stars, Himiko stood apart, not just because of its size, but because it blazed with almost unnatural brightness. This brightness wasn't an illusion, nor was it a coincidence. It was driven by one of the most powerful and revealing forms of radiation in the universe, Lyman-alpha emission. And Himiko wasn't just emitting a little of it, it was flooding the cosmos with it, making it one of the brightest objects ever detected from that ancient epoch. Lyman-alpha radiation is a specific wavelength of ultraviolet light, produced when electrons and hydrogen atoms drop from the second lowest energy level to the lowest. In the dense, star-forming regions of a young galaxy like Himiko, massive stars pour out ionizing radiation, stripping electrons from surrounding hydrogen atoms. When these electrons recombine with protons, they cascade down through energy levels, and in doing so, emit photons, often at the precise frequency of Lyman-alpha. This creates a glow, a telltale sign that intense star formation is underway. But here's where the story becomes even more intriguing. The early universe, during the time Himiko existed, wasn't exactly a welcoming place for Lyman-alpha photons. Back then, the cosmos was filled with clouds of neutral hydrogen, gas that readily absorbed and scattered Lyman-alpha light. Most young galaxies, no matter how luminous they were intrinsically, had their Lyman-alpha emissions muffled, dampened, or blocked altogether by this cosmic fog. So, for Himiko to shine as brightly as it does in Lyman-alpha light is nothing short of astonishing. This brightness meant that Himiko was producing massive amounts of high-energy ultraviolet radiation, likely from clusters of young, hot, massive stars. These stars lived fast and died young, ending in supernova explosions that seeded the surrounding gas with heat and turbulence. Yet the light from these stars, filtered through the galaxy's ionized gas, emerged with such intensity that it pierced the neutral hydrogen haze of the universe and traveled for over 12.9 billion years to be detected by modern telescopes. The brightness also tells us about Himiko's star formation rate. Based on the strength of its Lyman-alpha emission, astronomers estimate that Himiko was forming stars at an astonishing rate, possibly 100 solar masses per year. That's more than 100 times the current star formation rate of the Milky Way. For a galaxy in the cosmic dawn, that number is mind-blowing. It suggests that Himiko was a veritable forge, converting pristine hydrogen gas into blazing, short-lived stars at a furious pace. What's even more remarkable is how extended this Lyman-alpha glow appears to be. Unlike many early galaxies, where Lyman-alpha radiation is concentrated around compact star-forming cores, Himiko's emission is broad and diffuse, stretching tens of thousands of light-years across. This suggests that the ionized gas surrounding the galaxy is not only extensive, but also relatively transparent, again, a strange feature for a time when the universe was still transitioning from darkness to light. One of the puzzling aspects of Himiko's brightness is the lack of dust. In most modern galaxies experiencing rapid star formation, the resulting supernovae and stellar winds produce lots of heavy elements and dust. That dust absorbs ultraviolet light, including Lyman-alpha photons, and re-emits it in the infrared. But Himiko appears to be largely dust-free. This allows its Lyman-alpha light to escape more easily, without being swallowed up or converted into other wavelengths. This absence of dust could be because Himiko formed its stars from relatively unenriched, primordial gas, a feature consistent with an early, metal-poor galaxy just beginning to chemically evolve. This purity, this raw, unfiltered brightness, gives us a rare and precious window into the mechanics of the early universe. Himiko isn't cloaked in the complex recycling of gas and dust that characterizes later galaxies. Its light is elemental, primitive, and intense. And that makes it an incredibly valuable object for study, because it allows astronomers to observe early star formation in a cleaner, less obscured environment than they usually encounter. The magnitude of Himiko's Lyman-alpha emission is also what led to its classification as a Lyman-alpha blob, a rare and still poorly understood class of objects that emit vast amounts of this radiation across large spatial regions. Most Lyman-alpha blobs have uncertain origins. Some are believed to be powered by massive starbursts. Others may be linked to active galactic nuclei, or even to cold accretion flows, streams of pristine hydrogen gas funneled directly into forming galaxies from the intergalactic medium. Whatever the mechanism, Lyman-alpha blobs are special, and Himiko was among the first and most distant ever found. From a practical standpoint, Himiko's brightness in this wavelength made it easier to observe and study than most other high redshift galaxies. Astronomers were able to measure its redshift, determine its distance, and infer its properties with a degree of certainty that is rare when dealing with such distant targets. The Lyman-alpha line, because of its distinctive position in the spectrum, acts like a cosmic ruler. When it shifts toward longer wavelengths due to cosmic expansion, it provides a precise indication of how far the galaxy's light has traveled, and therefore, how old the light is. Himiko's Lyman-alpha redshift, put it firmly at Z, is almost equal to 6.6, or roughly 800 million years post-Big Bang. In a universe still groaning under the weight of hydrogen fog, Himiko was already a beacon. Its radiation carved a path through the neutral hydrogen, forming a kind of cosmic tunnel through which its light could escape. This process may have been aided by so-called ionized bubbles, regions around the galaxy where radiation from massive stars had ionized the surrounding gas, clearing out a transparent pocket in the intergalactic medium. Within such a bubble, Lyman-alpha photons would face fewer obstacles, traveling farther and more freely into space. But even with these explanations, Himiko remains a puzzle. Why is it so luminous? Why does it lack dust? How does its Lyman-alpha emission remain so strong, even in an environment that should scatter and absorb such radiation? These questions don't diminish its value, they enhance it. Because in answering them, we learn not only about Himiko, but about the early universe itself. We gain clues about how galaxies form, evolve, and interact with their surroundings in a time when the cosmic rules were still being written. Himiko is more than a bright object from the past. It is a kind of flare launched from the depths of cosmic infancy, illuminating the surrounding darkness and screaming across time. Look at me! I should not exist, and yet here I am. As astronomers zoomed in on Himiko with the best observational tools available, they began to notice something strange. Not just the glow, not just the intensity, but the structure hidden within its expansive light. Himiko was not a single, smooth, centralized beacon. Instead, it revealed a broken silhouette, fragmented into three distinct bright clumps scattered across its wide Lyman-alpha glow. These were not minor irregularities. Each of these clumps shone with its own power, bright enough that, under different circumstances, each could be mistaken for an independent galaxy. And yet, here they were, locked together inside a common gaseous envelope, forming what appeared to be a single, massive system. This triple-core structure was unexpected. In most early galaxies observed at such a distance, the visible structure is compact and often unresolved, either a faint dot or an elongated smear of starlight, barely distinguishable from background noise. But Himiko's core stood out. Not one clump, not two, but three luminous regions, each radiating strongly in ultraviolet and Lyman-alpha emission, each a potential seat of intense star formation. The leading interpretation is that these are three galaxies in the process of merging. In the early universe, galactic mergers were common and often necessary. Smaller galaxies collided and coalesced to form the larger systems we see today. But such mergers usually leave chaotic trails of gas, irregular shapes, and disrupted structures. Himiko's clumps, while irregularly spaced, don't appear chaotic. They are each bright and condensed, and the entire system is enveloped in a uniform Lyman-alpha halo, as though bound together in a shared gravitational dance. It's possible we are witnessing a rare moment of synchronized star formation, triggered by the gravitational interactions between these clumps, proto-galaxies locked in a spiral toward union. Another possibility is that these are not separate galaxies but rather intense starburst regions within a single, enormous galaxy. These starburst regions would be knots of extreme stellar birth, where the gas density is high, the cooling is fast, and the star formation rate is pushed to the limit. Given Himiko's overall brightness and high star formation estimates, this is plausible. Each clump could contain millions of young, massive stars burning hot and short-lived, contributing to the galaxy's formidable Lyman-alpha output. But the most intriguing element of the triple-core observation is what it implies about the timeline of structure formation. If these are indeed merging galaxies, then Himiko is offering us a snapshot of the hierarchical formation process, caught in the act. Most of our understanding of early mergers is derived from computer simulations and indirect evidence. Here, we have something direct, a real-time look at what could be the birth of a supergalaxy. The eventual result of this merger might be something more massive than any single component, an early elliptical or a massive irregular galaxy, depending on how the dynamics unfold. One of the puzzles surrounding this triple-core configuration is how such a complex structure managed to form so soon. These clumps aren't wisps of loosely bound gas. They are compact and bright, hinting at concentrated mass and robust star-forming capacity. To see them already assembled and interacting within the first 800 million years of cosmic history again raises the question, is this process more common than we realize, or is Himiko a rare anomaly? Adding to the mystery is how these cores are spaced. They aren't crammed tightly together in the center. There is separation between them, tens of thousands of light years, yet they remain within the diffuse emission zone, suggesting a gravitational association. This scale, when compared to the early universe, is enormous. It implies that whatever dark matter halo surrounds Himiko must be massive and expansive enough to bind these cores together while still allowing them the room to develop their own internal structures. Furthermore, the interactions between these clumps might be the very reason Himiko is so luminous. In galactic dynamics, tidal forces during a merger compress gas clouds and drive them toward the centers of galaxies, triggering explosive star formation. If all three clumps are undergoing such a process simultaneously, that could explain the extraordinary rate of star formation and the extreme Lyman-alpha output. It's not just that Himiko is large and bright, it's that it might be caught in a rare moment of triple-triggered galactic ignition, where all components are feeding off the same gravitational turbulence. The alignment and motion of these clumps are not yet fully understood, in part because their individual redshifts and velocities are difficult to measure at this distance. But future spectroscopic analysis, especially with instruments like the James Webb Space Telescope, could help determine whether the clumps are moving toward each other, orbiting in a complex gravitational system, or perhaps just aligned along the same line of sight. For now, the data suggests cohesion, and with that, the compelling vision of a triple-core galaxy in formation. Some scientists have even speculated about the presence of filamentary inflows, cold gas streams feeding into Himiko from the cosmic web. In this model, the three clumps could represent nodes where gas accumulates at intersections of these streams, forming stars at accelerated rates. The triple-core structure, then, would not be a product of merging but of simultaneous, localized gravitational collapse driven by large-scale cosmic flows. Regardless of which interpretation holds true, the triple-core feature sets Himiko apart. It adds another layer to its already baffling nature, not just size, not just brightness, but internal complexity in a time when simplicity was expected. Himiko isn't just early, it's evolved. It shows signs of galactic behaviors we thought took billions of years to emerge. And it brings to light a more philosophical question: if such complexity can exist so early, what else have we missed in the dark reaches of the cosmic dawn? How many other multi-core, star-forming giants are hidden just beyond our detection limits? Himiko's three bright clumps are more than just structural oddities. They are messages from the past, challenging us to rethink the speed, mechanics, and diversity of galactic evolution in the universe's first billion years. As the light from Himiko continued to be analyzed, scrutinized across wavelengths, dissected by spectrographs, and modeled against our best simulations, an increasingly provocative question began to emerge: are we witnessing a galactic merger in action? The possibility, though still debated, presents a tantalizing narrative, one in which Himiko is not a single, unified object but rather the collision site of multiple early galaxies, drawn together by gravity in one of the universe's earliest large-scale interactions. If true, it would not only explain many of Himiko's peculiar properties but also elevate it to one of the most important cosmic laboratories we've ever observed. In today's universe, galactic mergers are a well-known phenomenon. Massive spirals collide and form elliptical giants. dwarf galaxies are swallowed by larger ones. Tidal forces rip stars from their orbits, gas clouds compress into waves of new star formation, and over time, the violent chaos settles into a new cosmic identity. But this entire process is usually thought to occur over billions of years. It's slow, graceful, and stretched out across epochs. What makes Himiko so stunning is that it appears to be doing all of this just 800 million years after the Big Bang, when the cosmic clock had barely started ticking. The three bright clumps observed in Himiko's structure could very well be independent galaxies in mid-collision, proto-galaxies merging into a single, much larger structure. In this scenario, each of the clumps began as its own gravitationally bound region, forming stars from collapsing gas in isolation. Over time, mutual gravitational attraction pulled them together, drawing them into a complex dance of spirals, orbits, and eventual coalescence. The turbulence of this interaction would compress the gas in each system, ignite starbursts, and create the high rates of star formation inferred from Himiko's brightness. This would also help explain the extended Lyman-alpha halo. Galactic collisions often produce massive, heated envelopes of ionized gas that glow brightly in this wavelength. It might even account for Himiko's unusually dust-free nature. If the galaxies are still in the early stages of merging, they may not yet have had time to accumulate the metals and dust typically produced in later starburst stages. Everything would be happening in fast-forward, as though the universe had temporarily put evolution on double speed. But this isn't just speculative hand-waving. Simulations of the early universe suggest that massive galaxies like the Milky Way may have formed through a series of rapid, high-redshift mergers, small clumps of matter collapsing under gravity, interacting violently, and assembling into larger halos in a relatively short time. Himiko might be our first direct evidence of this process frozen mid-step, a visual confirmation of the theory that galactic collisions were not only common in the early universe but were essential to the creation of the massive systems we see today. However, even within this context, Himiko is still extraordinary. Most mergers observed at this redshift are far less massive, far less luminous, and far less coherent. Himiko's components are bright, its structure is vast, and its emission is continuous and powerful. That raises questions. Was Himiko's merger environment unusually favorable? Did it form in an especially dense part of the early cosmic web, where dark matter filaments funneled vast reservoirs of gas and proto-galaxies into a single point? The idea of filament-fed mergers has gained traction in recent years. In this framework, the large-scale structure of the universe, the cosmic web of dark matter and gas, acts as a skeleton, with galaxies forming and moving along its strands. Where filaments intersect, matter accumulates rapidly. Himiko could be located at one such intersection, experiencing an inflow of cold gas from multiple directions while simultaneously pulling in nearby galaxies. This setup could naturally result in a rapid, large-scale merger that bursts a super-galaxy before the rest of the universe has even begun to wake up. Another point supporting the merger hypothesis is the lack of an active galactic nucleus, AGN. In many early galaxies undergoing rapid evolution, a central supermassive black hole feeds on infalling gas, producing enormous jets and X-ray radiation. Yet Himiko doesn't show strong signs of this kind of activity. That might suggest that the galaxy is still in the early phases of merging, before the central black hole has formed or been fully fed. It might even hint at a unique path of galactic evolution, one where black hole formation follows, rather than precedes, massive star formation and structural assembly. Importantly, if Himiko really is a galactic merger in progress, it gives us a rare snapshot of time that's usually too brief and too dim to capture. Mergers don't last long, especially in the fast-paced early universe. Once the galaxies combine, their distinct identities blur, and what remains is a single, more massive system that carries few traces of its chaotic past. Catching Himiko during the act would be like finding a fossilized heartbeat, an instant of transformation preserved in light. But Himiko doesn't just offer answers. It challenges our understanding of how common such early mergers might be. If Himiko is rare, then it might represent a statistical anomaly, an outlier on the far edge of possibility. But if future telescopes like JWST discover more such systems, it would mean that our models of galaxy formation are too conservative. It would mean that the early universe was not just forming stars and galaxies. It was fusing them at high speed, creating massive systems through violent collisions long before we thought it possible. What makes this even more compelling is that we are not just looking at Himiko, we are watching it become. The light that reaches us today is a live record of a merger happening 12.9 billion years ago. Those three clumps may now be one. Or they may have been torn apart. The galaxy Himiko, as it exists today, is unknowable to us. Its present is forever beyond our reach. But the past we see is rich, dynamic, and full of motion. It is a moment of birth, destruction, and synthesis all at once. Whether Himiko is a snapshot of three galaxies merging, a single fragmented system undergoing internal upheaval, or something even stranger, its message is clear. Galaxies could grow fast and violently, even when the universe was young. In Himiko's light, we see a contradiction, a collision between theory and reality, between what should be and what is. The more astronomers stared into the depths of space to understand Himiko, the more it became clear that this object was unlike most others from its time, or any time. It wasn't just a bright galaxy. It wasn't just large or clumpy or old. Himiko's glow was something else entirely. It wasn't contained, or sharply defined like typical galaxies. Instead, it was vast and ghostly, like a spectral cloud suspended in the darkness of the early universe. This immense, diffuse brightness wasn't a trick of the instruments, or an illusion of distance. It was a real feature, one that would lead scientists to classify Himiko as one of the earliest and most distant examples of a mysterious class of astronomical objects known as Lyman-alpha blobs. Lyman-alpha blobs, or labs for short, are enormous clouds of glowing hydrogen gas, often stretching hundreds of thousands of light-years across. They emit strongly in the Lyman-alpha line, a specific frequency of ultraviolet light released when hydrogen atoms are ionized and then recombine. These blobs are not fully understood. In fact, they're one of the more puzzling categories of extragalactic phenomena. They can shine brighter than entire galaxies, but they often lack obvious central engines like supermassive black holes or fully formed galactic cores. Some are associated with galaxies. Others seem to hover in space, glowing without a clearly defined source of illumination. Himiko fits right into this enigmatic mold. Its Lyman-alpha emission isn't just strong, it's sprawling. The halo of ultraviolet light radiating from Himiko extends far beyond the visible cores of the galaxy. This is not the tidy, centralized emission we see from young star clusters or galactic nuclei. This is wide, faint, and spatially extended, glowing tens of thousands of light-years beyond what we'd normally expect from a galaxy that early in the universe's history. It's this feature, the sheer size and diffusion of its glow, that earned Himiko its place among Lyman-alpha blobs. And for an object observed at Z6.6, this is extraordinary. Most labs have been found at redshifts between 2 and 4, meaning they appear when the universe was about 2 to 3 billion years old. Himiko, by contrast, was already a luminous blob when the universe was only about 800 million years old. It didn't just belong to this class, it predated almost all of them. It became a kind of primordial prototype for what a Lyman-alpha blob might look like in the universe's earliest epoch. But what causes such diffuse emission? That question has haunted astronomers for decades. In Himiko's case, several theories have been proposed. One of the most straightforward ideas is that the Lyman-alpha glow is the product of intense star formation. The clumps within Himiko are forming massive, young stars, which flood the surrounding gas with ionizing radiation. When the hydrogen recombines, it emits Lyman-alpha photons, creating a large emission region around the galaxy. But this only explains part of the phenomenon. The glow is too large and too uniform to be accounted for by internal star formation alone, especially since star-forming regions are usually more concentrated and irregular in their structure. Another possibility is cooling radiation. In this scenario, the gas surrounding Himiko is still in the process of collapsing into the galaxy. As it falls inward, it heats up and radiates away that heat in the form of Lyman-alpha photons. This would explain the smooth, extended halo, an enormous reservoir of primordial gas bleeding energy as it condenses, slowly feeding the galaxy and lighting up the space around it. This process might be particularly efficient in the early universe, where cold, dense gas flows directly into galaxies along the filaments of the cosmic web. Yet another explanation invokes galactic superwinds. Himiko is likely undergoing rapid star formation, and that starburst activity can drive powerful outflows of gas. These outflows can shock and heat the surrounding medium, creating a cocoon of energized hydrogen that glows brightly in Lyman-alpha. However, this would typically create more irregular structures, fingers or shells of gas extending outward in different directions. Himiko's glow, by contrast, appears more continuous and symmetrical, suggesting a steadier, more uniform source of ionization. One more intriguing possibility is that Himiko is being illuminated by the reionization of the intergalactic medium itself. During the Epoch of Reionization, ultraviolet photons from the first stars and galaxies began ionizing the hydrogen that filled the cosmos. This was a chaotic, patchy process, with bubbles of ionized gas forming around the earliest luminous objects. Himiko could be at the center of one such bubble, ionizing its surroundings and creating a large region of transparent space through which its Lyman-alpha photons could travel more freely. In this view, the blob isn't just a feature of Himiko, it's a footprint of cosmic reionization, one of the largest structural changes the universe has ever undergone. But even with all these ideas, there is no consensus. Himiko's status as a Lyman-alpha blob leaves us with more questions than answers. Why is it so luminous without an active galactic nucleus? Why is it so extended without a clearly chaotic merger halo? Why is it visible at all in an epoch when neutral hydrogen should have absorbed much of its light? The object is defying the templates we've built over decades of research, templates based on lower redshift blobs, galaxies, and quasars. Himiko sits outside the curve, glowing with a kind of quiet, relentless intensity. It's also important to remember what this means observationally. Most early galaxies at Z greater than 6 are barely detectable. They show up as faint smudges in deep field surveys, ghosts at the edge of our instrumental sensitivity. Himiko, by contrast, is blazing. Its diffuse emission makes it easier to detect with narrowband imaging techniques that target the Lyman-alpha line. Without this glow, Himiko might have gone unnoticed, blending into the cosmic background like so many of its fainter peers. But its light reached us, not as a single point, but as a cosmic fog, hanging silently in space, drawing attention through sheer scale. As one of the earliest known Lyman-alpha blobs, Himiko has become a benchmark. It's used in models, cited in papers, and revisited in simulations. It's a warning that even our best theories are built on incomplete observations. And it hints at a broader population of similar objects that may still lie undetected, waiting for future telescopes to bring them to light. In time, we may find that Himiko is not alone. Perhaps there are other luminous blobs from the cosmic dawn, quietly glowing in the ultraviolet, hidden behind redshift and distance and time. But for now, Himiko remains a solitary beacon, burning diffuse and beautiful, a rare, early whisper from the universe's deepest silence. Long before galaxies like the Milky Way took shape, before the first planets coalesced from star-forged elements, and even before space itself was transparent, there was a pivotal era in the history of the cosmos, a transformative chapter known as the Epoch of Reionization. It was during this obscure and tumultuous time, roughly between 400 million to 1 billion years after the Big Bang, that the universe underwent one of its most profound changes. It became transparent to light. And it was during this very phase that Himiko emerged, a beacon glowing defiantly through a cosmos still thick with primordial fog. The Epoch of Reionization marked the end of what cosmologists call the cosmic dark ages. After the initial light of the Big Bang faded and the universe cooled, it was plunged into darkness for hundreds of millions of years. During this time, hydrogen atoms, which had formed when the universe cooled enough for protons and electrons to combine, filled the cosmos. These neutral hydrogen atoms absorbed light in the ultraviolet and optical ranges, preventing it from traveling far. The universe was effectively opaque. But as the first stars and galaxies began to form, they emitted high-energy ultraviolet radiation, light capable of reionizing hydrogen, stripping away its electrons and transforming the gas into a transparent plasma. Over time, these ionized bubbles grew, merged, and spread, turning the opaque universe into one that allowed light to traverse vast cosmic distances. It was the dawn of visibility, the moment when the universe began to shine in earnest. Himiko formed right in the midst of this era, at c 6.6, or about 800 million years after the Big Bang. That puts it squarely in the late stages of reionization, a critical moment when the balance between light and shadow was tipping toward illumination. The fact that we can see Himiko at all is remarkable. It means that either it resides within a sufficiently large ionized bubble where light can escape, or that it played an active role in carving out such a bubble with its own intense radiation. This makes Himiko not just an object from the past, but a window into one of the universe's greatest transitions. By studying the properties of Himiko's light, especially its Lyman-alpha radiation, astronomers can learn about the intergalactic medium it passed through. That light, after traveling nearly 13 billion years, carries the fingerprints of the space it moved through. Was the region around Himiko already ionized? Was the Lyman-alpha line shifted, absorbed, or scattered? These questions allow scientists to map the structure and patchiness of reionization, to see which areas of the early universe lit up first and how that light spread. But why does this matter? Because reionization wasn't uniform. It didn't happen everywhere at once. It was a patchy, irregular, uneven process, like a fog lifting from a forest in scattered, glowing pockets. Some galaxies were trapped in still neutral regions, their light absorbed and lost. Others, like Himiko, either formed in more evolved neighborhoods or burned bright enough to ionize their surroundings. Himiko may have been a local architect of transparency, one of the engines that drove the great clearing of the cosmic skies. Its immense Lyman-alpha halo supports this idea. The Lyman-alpha photons, notoriously easy to scatter in neutral hydrogen, shouldn't travel far unless the surrounding medium is already largely ionized. Himiko's success in shining through suggests it existed within a substantial ionized region, either created by its own stellar radiation or shared with nearby, perhaps unseen, galaxies. In this sense, Himiko acts like a lighthouse on a rising coast, illuminating the fog around it and marking a new phase of cosmic evolution. Moreover, Himiko's potential to reionize space isn't just a poetic idea, it's a quantifiable question. Astronomers estimate that to reionize the universe, galaxies needed to produce an enormous number of ionizing photons. Whether typical galaxies at the time could do this remains under debate. Himiko, however, might represent a class of galaxies that overperformed, producing light at such a furious rate that they became key players in the reionization narrative. Its high star formation rate, possibly 100 solar masses per year, means it hosted a vast population of young, hot stars, each capable of flooding the cosmos with ionizing radiation. But the story doesn't end there. Himiko also challenges assumptions about galaxy evolution during reionization. Models had predicted that galaxies in this era would be small, faint, and metal-poor, incrementally building toward complexity. Himiko is large, luminous, and structured, suggesting that galactic development was more advanced and more variable than previously thought. This complicates the reionization picture. If galaxies like Himiko were more common than expected, then the process of reionization may have unfolded more quickly or through different mechanisms than our simulations have anticipated. Furthermore, Himiko could provide insights into the end stages of reionization. By Z6, much of the universe was already transparent, but not uniformly so. Studying objects at this redshift helps fill in the gaps. It's like looking at the final stars of twilight before full sunrise. Himiko's light contains evidence of the last remnants of cosmic fog and the emergence of large, fully ionized zones. The way Himiko's Lyman-alpha line is shaped and shifted offers a kind of cosmic weather report on the state of the intergalactic medium. Is the line symmetrical or asymmetric? Is there a damping wing, an extended red tail that would indicate neutral hydrogen still absorbing some light? These subtle details are carefully analyzed by astronomers, pixel by pixel, spectrum by spectrum, to decode the transparency, or opacity, of the universe in Himiko's direction. Every nuance of its light helps refine our map of when and where reionization occurred. So in Himiko, we don't just see a galaxy. We see a process. We see an age. Himiko is not merely a relic from a formative time. It is an active witness to the universe's transformation, and possibly a participant in that transformation. Its photons may have helped break the darkness. Its glow may have pushed the boundary of visibility outward. And its story, preserved in ancient light, is now a tool for unlocking one of the greatest mysteries in all of cosmology. How did the universe become visible? In the shimmering contours of Himiko's extended light, in the redshifted whisper of its Lyman-alpha glow, and in the silence it broke after hundreds of millions of years of darkness, we find a profound truth. This galaxy is a bridge between blindness and sight, between chaos and clarity, between what the universe was and what it would become. When we look at Himiko, we are witnessing not just a luminous glow from deep space, but a factory, one of the most ancient and industrious star-making machines the cosmos has ever revealed. The intense brightness, particularly in the ultraviolet and Lyman-alpha emissions, tells a story of ceaseless stellar birth. Himiko isn't quietly twinkling like most early galaxies. It is blazing with the collective fire of tens of thousands of young, massive stars, forming at a rate that leaves even modern galaxies humbled. Estimates suggest it may be churning out new stars at a staggering pace of 100 solar masses per year, an astronomical figure especially for a galaxy that existed when the universe was less than 1 billion years old. To grasp the magnitude of this, consider our own Milky Way. It forms stars at an average rate of about 1 to 2 solar masses per year. And that's in a mature, stable, metal-rich spiral galaxy with over 13 billion years of evolution behind it. Himiko, by contrast, existed during the cosmic equivalent of infancy, when conditions for star formation were thought to be far more primitive and less efficient. Yet here it is, forming new suns at nearly 100 times the rate of our entire galaxy today. That kind of productivity places Himiko among the elite class of what astronomers call starburst galaxies, those undergoing intense, short-lived periods of rapid star creation. This frenzied rate of stellar birth suggests that Himiko is loaded with cold, dense gas, hydrogen, primarily, which is the raw fuel for star formation. In the early universe, galaxies had access to pristine reservoirs of gas funneled in from the intergalactic medium. But even so, the gravitational compression, cooling, and collapse of that gas into stars at such a scale would require an extraordinarily efficient set of conditions. The presence of multiple bright clumps in Himiko, each potentially a site of concurrent starburst activity, may be a key reason for this. It's possible that gravitational interactions or a merger event triggered a domino effect, compressing vast clouds of hydrogen across the galaxy and setting off synchronized waves of star formation. In such a scenario, the entire galaxy would become a stellar nursery. Massive stars, many tens of times the size of the Sun, would ignite within just a few million years of their formation. These stars burn hot and bright, emitting copious amounts of ultraviolet radiation and driving powerful stellar winds. Eventually, they explode as supernovae, enriching the surrounding gas with heavier elements and injecting energy into the interstellar medium. But in Himiko's case, the process may still be in its early stages. The intense brightness, the apparent lack of dust, and the absence of widespread metal lines in its spectrum suggest we may be seeing a first-generation starburst, a population of stars forming out of mostly pristine hydrogen and helium, untouched by the remnants of earlier generations. These stars would not only light up the galaxy, they would transform it. Their radiation would ionize vast swaths of surrounding gas, contributing to Himiko's enormous Lyman-alpha halo. Their supernovae would stir the interstellar medium, potentially disrupting future star formation in some regions while triggering it in others. The feedback from such an event is complex, chaotic, and short-lived. Starbursts rarely last more than a few 100 million years. And yet, in that brief time, they can generate hundreds of millions of stars and reshape the entire structure of a galaxy. It's even possible that Himiko is forming some of the earliest globular clusters, dense, spherical collections of stars that we still see in galaxies like the Milky Way today. If so, those ancient clusters could still exist, preserved across cosmic time, holding stars born in the fire of this early inferno. The star formation rate also provides indirect evidence about Himiko's mass. In order to support such intense activity, the galaxy must have a substantial gravitational pull, likely provided by an underlying dark matter halo. Without that deep gravitational well to hold on to gas and maintain pressure, the energetic processes inside Himiko, supernovae, stellar winds, radiation pressure, would quickly blow the gas away, halting star formation. The fact that Himiko is sustaining its starburst means it is anchored by something massive and stable, yet still invisible to our telescopes. This further deepens the mystery of how such a large, stable, and prolific galaxy formed so early. One major implication of this ancient star factory is its potential contribution to cosmic reionization. Each massive star produces vast numbers of ionizing photons. Himiko, with thousands or even millions of such stars forming rapidly, may have pumped enough energy into its surroundings to ionize a significant bubble of the intergalactic medium. It wasn't just forming stars for its own growth. It may have been actively shaping the structure and transparency of the young universe around it. But like all starburst galaxies, Himiko is probably not destined to remain this productive forever. The gas reservoirs that fuel such activity can only last so long. Either they'll be consumed by star formation, or blown away by the energetic winds and explosions that follow. This means we are seeing Himiko in a brief, luminous window, a flash of intense activity that will eventually settle, fade, and evolve into something calmer, more structured, and more familiar. But that moment of intense creation is exactly what makes Himiko so valuable to astronomers. It provides a snapshot of galactic growth in its most energetic, unrestrained phase. Moreover, the simplicity of its gas composition, still largely hydrogen and helium, suggests these stars may resemble the population 2 or even population 3 stars, theoretical first-generation stars formed from the purest gas in the universe. While direct evidence for population 3 stars remains elusive, galaxies like Himiko offer one of the best chances to study environments where such stars could exist. If Himiko contains these ancient stellar ancestors, it would be a link to the very first structures ever to shine, offering clues to the origin of light, structure, and complexity in the cosmos. Himiko, then, is not just bright for its time. It is bright because it is one of the first galaxies to reach such an extreme phase of activity. It burns as a testament to how rapidly the universe organized itself into structure, and how quickly light fought back the dark. As a star factory, it is a furnace on the edge of time, mass-producing the very engines of future solar systems, planets, and perhaps even life. In a universe filled with violent births and fiery deaths of stars, dust becomes an inevitable byproduct. Tiny grains forged in the hearts of dying stars, spewed into space by supernovae and stellar winds, and eventually woven into the next generation of stars and planets. In most starburst galaxies, especially those forming stars as rapidly as Himiko, this dust is a signature trait. It absorbs ultraviolet light and re-emits it in the infrared, cloaking the galaxy in a shroud of warm, glowing material that astronomers often use to trace star-forming activity. But Himiko defies this rule. Despite its furious pace of star formation, an astonishing 100 solar masses per year, observations reveal that it is, quite unexpectedly, nearly dust-free. This absence of dust is not subtle. It is stark. Observations with the Spitzer Space Telescope and follow-ups using submillimeter instruments sensitive to dust emissions failed to detect significant dust content within Himiko's massive structure. The galaxy's spectral energy distribution, essentially a map of how it emits light at different wavelengths, shows little of the telltale signs of warm dust. This is highly unusual, especially for a galaxy that is not only luminous but undergoing what should be an intensely turbulent period of evolution. This discrepancy has forced astronomers to reevaluate some of their core assumptions. Under normal circumstances, young, massive stars, the kind Himiko is forming in vast quantities, live fast and die young, exploding as supernovae in just a few million years. These explosions are expected to enrich the interstellar medium with heavier elements, including carbon, oxygen, silicon, and iron, all critical ingredients in dust formation. So if Himiko is indeed full of such stars, where is all the dust? One possibility is that Himiko's starburst is extremely young. The stars may have only recently begun to form en masse, and the first generations may not yet have ended their lives in supernova explosions. If the bulk of the stars are less than about 10 million years old, the dust-producing phase of stellar evolution, when red supergiants and supernovae start to flood the galaxy with metals, might not have had time to begin. This would place Himiko at a very specific and very brief moment in its evolution, a cosmic blink in which stars are blazing into existence, but dust hasn't yet caught up. Another possibility lies in the metallicity of Himiko's gas, which is likely very low. In the early universe, most gas was composed almost entirely of hydrogen and helium. Heavier elements, or metals, in astronomical terms, were formed later through nucleosynthesis in stars and supernovae. Himiko's low metal content means that even if its stars are dying and exploding as expected, the raw materials for efficient dust production, carbon, silicon, and iron, are simply not present in sufficient quantities. The dust factories haven't been fully stocked yet. This raises an intriguing thought. What if Himiko is revealing a primordial mode of galaxy evolution, one not heavily influenced by the recycled products of stellar generations past? Most galaxies we observe, even at modest redshifts, already show significant dust enrichment, having been shaped by countless cycles of star formation and destruction. Himiko might be among the rare few caught in that initial, unpolluted burst of formation, when galaxies built stars from nearly pure hydrogen and helium, untainted by the detritus of previous stellar lives. The lack of dust also has practical observational consequences. It means that much of the light Himiko emits, particularly in the ultraviolet, is not being absorbed and re-emitted, allowing it to shine more clearly and directly than dust-rich galaxies. This is likely part of the reason why Himiko was detected in the first place. Many dusty starbursts at similar redshifts remain hidden to optical and ultraviolet telescopes, visible only in the infrared and sub-millimeter bands. Himiko, by contrast, glows unfiltered in the Lyman-alpha and UV spectrum, making it a kind of cosmic lighthouse, easier to spot across vast distances. Yet this clarity comes with a downside. Without dust to trace the heating effects of young stars, astronomers have fewer tools to understand the galaxy's internal processes. They must rely more heavily on models, on interpretations of emission lines, and on careful cross-wavelength comparisons. The very transparency that makes Himiko visible also makes it elusive, its internal workings veiled in the blinding brightness of unobstructed starlight. There's also a fascinating astrophysical implication here. Dust plays an important role in shielding molecular gas from harsh radiation, allowing it to cool and collapse into new stars. Without much dust, Himiko's interstellar medium may be less protected, meaning that gas might be more easily ionized or heated by nearby stars. And yet, despite this, Himiko is forming stars at an extreme rate. This suggests either an unusually efficient cooling mechanism at play, or that the gas is being replenished at such a rapid pace that star formation continues regardless of conditions that would normally suppress it. In short, Himiko might be forming stars in a way that is fundamentally different from modern galaxies. It may represent a phase where dust and metals are not yet the regulators of star birth, but where gravity, turbulence, and primordial gas dynamics still dominate. This makes Himiko not just an early galaxy, but a glimpse into an alien version of star formation, one largely invisible in the local universe today. And then there's the future. Himiko may be in a temporary phase, a quiet before the dusty storm. If it continues forming stars at this rate, the inevitable result will be a population of supernovae that enrich the surrounding medium. Over time, this will lead to the gradual buildup of dust, shifting Himiko's appearance in the far infrared, changing its cooling dynamics, and perhaps even ending the very burst of activity that defines it now. We may be seeing Himiko before it becomes hidden, a rare, early snapshot of a galaxy on the cusp of transformation. That moment, this moment, matters. Because by catching Himiko in this dust-free phase, we are watching the cosmic canvas before the brush of time has painted over its clearest lines. The light we see is pure, direct, and ancient, untouched by the fine grains that usually cloud our view. Himiko is the starlight of a universe not yet dimmed by its own complexity, and in that transparency lies a form of raw, unsheltered truth. One of the most surprising aspects of Himiko, a galaxy so massive, bright, and seemingly advanced for its time, is what it appears to be missing. Despite its enormous size and intense activity, there is no strong evidence for the presence of a supermassive black hole at its core, no telltale signs of an active galactic nucleus, no jets, no powerful X-ray emissions, no high-energy outflows typically associated with accretion processes. This absence is both puzzling and profoundly important, because in the modern universe, virtually every large galaxy, especially ones as massive as Himiko appears to be, hosts a supermassive black hole at its center, often weighing millions to billions of times the mass of the Sun. The link between galaxies and their central black holes is not a minor one. Over the past few decades, astronomers have discovered a near-universal relationship between the mass of a galaxy's bulge and the mass of its central black hole. This suggests that galaxies and black holes grow together, influencing each other's evolution in a codependent, perhaps even synchronized, dance. Supermassive black holes may regulate star formation through feedback mechanisms, blowing out gas and heating interstellar material with jets and radiation. And in turn, the galaxy feeds the black hole with matter from mergers, inflows, and dying stars. It's a tightly woven story, so tightly woven, in fact, that it's startling when we find an exception. Himiko may be one of those exceptions. Despite being observed in multiple wavelengths, including optical, infrared, and radio, there's no indication of the energetic behaviors typically seen in active galactic nuclei, AGN. AGNs are incredibly luminous sources powered by matter falling into a black hole. As that material spirals inward, it heats up, sometimes reaching millions of degrees, producing X-rays and ultraviolet light, and often launching massive outflows at relativistic speeds. None of that is evident in Himiko. Its light is dominated by star formation, not black hole activity. This could mean a few things. One possibility is that Himiko simply doesn't have a central supermassive black hole, at least, not yet. That would make it an even more unique laboratory for early galaxy formation. It would suggest that galaxies can grow to substantial size and complexity before developing central black holes, appending models that assume black hole formation begins early and grows alongside the host galaxy. It could even point toward multiple pathways of galactic evolution, where some galaxies become starburst beacons without the gravitational anchor of a black hole at all. Alternatively, Himiko might harbor a black hole that is currently dormant, either because it hasn't accumulated enough mass to ignite significant accretion, or because it is located in a part of the galaxy where gas inflows are inefficient. Unlike the spectacular quasars we've observed at similar redshifts, massive black holes devouring matter at rates that outshine entire galaxies, Himiko may represent a different evolutionary trajectory, one where stellar growth leads and black hole formation lags behind. There's also a third possibility. The black hole is present and even growing, but in a mode that's difficult to detect with current instruments. If the accretion rate is very low, or the surrounding gas is optically thick, the high-energy signals we associate with AGN activity could be absorbed or scattered. Himiko might be hosting a growing black hole buried deep within clouds of dense, ionized gas, hidden from view by the very starburst that makes the galaxy so bright. Yet even in this case, we would expect at least some indirect signatures, radio jets, mid-infrared excesses, X-ray flares, none of which have clearly emerged from observations so far. This silence speaks volumes. Because if Himiko really is without an active black hole, it forces us to reconsider our assumptions about when and how supermassive black holes formed. Traditionally, black holes were thought to arise from the remnants of the first massive stars. Population 3 stars collapsing into black holes that then merged and accreted matter, growing over cosmic time. Some models suggest that black holes could form directly from the collapse of gas clouds under the right conditions, skipping the stellar phase entirely. Either way, the expectation has been that early, massive galaxies should also contain early, massive black holes. Himiko's apparent lack of one challenges that view. It suggests that star formation and black hole growth are not necessarily simultaneous, nor guaranteed to be linked in the earliest epochs. Perhaps Himiko formed in a region of space with unusual conditions, low angular momentum, or asymmetric inflows, that allowed it to gather mass and form stars without feeding a central gravitational sink. Or perhaps it formed from the merger of smaller protogalaxies that hadn't yet developed black holes of their own. Another interesting consequence of Himiko's black hole silence is its impact on feedback mechanisms. In most starburst galaxies, black holes act as regulators, expelling gas, heating the interstellar medium, and quenching further star formation once the system becomes too active. Without a black hole doing this, Himiko may be in an unrestrained phase of growth, forming stars as fast as it can until internal feedback from supernovae and stellar winds becomes strong enough to halt the process. This could explain why its star formation rate is so high. It's unchecked, unregulated, and entirely driven by the availability of cold gas. That might also mean Himiko is short-lived in its current state. Without AGN feedback to stabilize its gas flows, it could burn through its fuel rapidly and then fade, leaving behind a massive but quiet galaxy that eventually evolves into a more conventional structure. Or perhaps it will eventually ignite a central black hole as conditions shift, and then begin the more familiar path of coevolution we see in other galaxies. Either way, the current moment, the moment we observe in Himiko's ancient light, shows a galaxy that is growing, glowing, and thriving without the gravitational heart we've come to expect. This discovery places Himiko in a rare category of galaxies that break the mold, offering us a snapshot of cosmic adolescence unfiltered by the usual assumptions. It invites deeper questions about diversity in galaxy formation, about the order in which cosmic structures assemble, and about how much we still don't understand about the birthplaces of black holes themselves. So as we gaze into the past and study Himiko's light, so pure, so ancient, and so unconventionally structured, we're reminded of how many paths evolution may take. Not every galaxy needs a dark core to shine brightly. Not every luminous object must be anchored by a cosmic monster. Sometimes, in the quiet spaces between the expected patterns, we find something extraordinary. Surrounding the luminous heart of Himiko is an immense, ghost-like shroud, an extended cloud of gas that stretches beyond the visible star-forming regions, diffusing into the cosmic background like vapor curling into the void. This vast, faint halo isn't just a beautiful visual. It is a vital key to understanding what Himiko is, how it formed, and what forces are shaping it from the inside out. As with so many other features of this enigmatic galaxy, this halo raises more questions than answers, each of them digging deeper into the puzzle of early cosmic evolution. At a glance, the presence of such an enormous gas halo might seem unremarkable. After all, galaxies are born from gas. But Himiko's halo isn't small or residual. It's enormous. Observations suggest that it extends tens of thousands of light years, larger than some entire galaxies at the time. It doesn't hug the central region tightly, nor does it show sharp boundaries or regular structures. Instead, it surrounds Himiko in a broad, diffuse envelope, glowing primarily through Lyman-alpha emission, the characteristic light given off by hydrogen atoms when they recombine after being ionized. This alone is significant. For Lyman-alpha photons to be emitted and escape such large distances, the surrounding environment must either be highly ionized or structured in a way that allows these photons to scatter out without being endlessly absorbed or deflected. That makes the gas halo both a physical structure, composed of real matter, and a luminous phenomenon, shaped by the light and energy Himiko itself is pouring out into space. Understanding what this halo is made of, where it came from, and how it behaves offers insight into some of the deepest processes of early galaxy formation. There are a few primary theories about the origin of Himiko's gas halo, and they aren't mutually exclusive. One leading idea is that the halo represents leftover primordial gas, material that collapsed under gravity to form Himiko in the first place but wasn't fully absorbed into stars or the denser parts of the galaxy. In this view, the halo is a fossil remnant of galaxy formation, the raw hydrogen that didn't quite make it into the central star factories. This would be consistent with simulations of early galaxy formation, which show cold gas streaming in along cosmic filaments, feeding proto-galaxies like Himiko with the fuel needed to ignite stars. If this is true, then Himiko's gas halo could be a direct glimpse of the cosmic web, a fragment of the massive hydrogen rivers that once connected and built the first galaxies. The halo, in this case, is not just part of the galaxy, it is part of the larger cosmic structure, still funneling matter inward as gravitational wells deepen. And its glow? That would be the result of energetic radiation from Himiko's young stars ionizing the infalling gas, causing it to emit Lyman-alpha photons and reveal its presence in ultraviolet light. But there's another possibility, one that speaks not to birth, but to feedback. Himiko's starburst activity is intense, and such rapid star formation inevitably comes with violent consequences. Massive stars live fast and die explosively, injecting energy into the interstellar medium through stellar winds and supernovae. This energy can heat surrounding gas, drive it outward, and push material into the galaxy's halo, or even into intergalactic space. This phenomenon is known as a galactic wind, and it is often seen in modern starburst galaxies, where it creates fountains or bubbles of outflowing gas that stretch thousands of light years. Could Himiko's halo be the product of such a wind? If so, it would suggest that the galaxy is already in the process of regulating itself. As stars form and die, their feedback prevents the next generation from forming too quickly, limiting runaway growth and setting the stage for a more balanced, mature structure. The gas in the halo would be enriched with elements from supernovae, carbon, oxygen, silicon, and possibly carry magnetic fields or turbulence imprinted by the explosion-driven chaos at the galaxy's core. Observing this gas in different wavelengths could help detect such enrichment, offering clues about how long the wind has been active and how far it has spread. A third explanation bridges the previous two. Himiko's gas halo may be both inflow and outflow, simultaneously drawing in fresh, cold hydrogen from the cosmic web while also pushing hot, ionized gas outward from stellar feedback. This complex, dynamic circulation would mirror what many simulations predict for early massive galaxies, an ecosystem of gas constantly cycling between star formation, enrichment, ejection, and accretion. In this model, the halo becomes a kind of cosmic exchange zone, a vast borderland where the past and future of the galaxy meet. And here's where the mystery deepens. The structure of the gas halo does not appear chaotic. It isn't marked by the jagged, asymmetric features you might expect from explosive events or multiple collisions. Instead, it is smooth, consistent, and quietly luminous. That smoothness challenges some of the more energetic galactic wind models, suggesting that if feedback is shaping the halo, it may be doing so gently, or that the wind is very young and hasn't yet imprinted visible disturbances on the surrounding gas. Alternatively, the halo may not be entirely Himiko's at all. It's possible that the three bright clumps seen in the galaxy are merging subgalaxies, and the halo is the shared gas envelope that surrounds this protocluster. In this case, we may be seeing the early stages of a larger structure forming, one that will eventually stabilize into a giant elliptical or spiral galaxy, but is still in the chaotic process of assembly. The gas halo would be the gravitational glue binding the system, slowly collapsing or dispersing depending on the outcome of the merger. The potential presence of cold gas flows is also particularly exciting. These are theoretical streams of pristine hydrogen flowing directly from the cosmic web into galaxies, bypassing the shock heating processes that dominate in larger, more evolved systems. If Himiko's halo is partially composed of such flows, it could be the first direct observational evidence of this long-predicted phenomenon. That would make Himiko not just a relic of early galaxy formation, but a direct participant in the cosmic infrastructure that built the modern universe. Future observations, especially with the James Webb Space Telescope and other next-generation instruments, may help disentangle these possibilities. By mapping the motion of the gas, its composition, its temperature, and its interactions with surrounding radiation, astronomers hope to determine whether the halo is static or dynamic, enriched or pristine, falling in or being blown out, or perhaps all of these at once. For now, it remains one of the most tantalizing features of an already extraordinary galaxy. Because in Himiko's vast, glowing shroud, we find not only the fingerprints of its formation but the echoes of the cosmos itself, hydrogen born in the Big Bang, caught in a moment between chaos and order, lit by the stars it helped create. It's a reminder that galaxies are never isolated. They are shaped by what surrounds them, by what flows through them, and by what lingers long after their fires ignite. The story of Himiko, the enigmatic, ancient galaxy blazing from the universe's early dawn, would have remained invisible to us if not for the combined power of two of NASA's most pioneering observatories, the Spitzer Space Telescope and the Hubble Space Telescope. Without these orbiting instruments, hovering above Earth's distorting atmosphere, the faint, redshifted glow of this distant object, emitted when the universe was only about 800 million years old, would never have been resolved in the way it has. Himiko's discovery, and the slow unraveling of its secrets, is as much a triumph of human engineering as it is a cosmic revelation. Himiko's light is ancient, so old, in fact, that it has been redshifted deep into the infrared portion of the electromagnetic spectrum. As the universe expands, light from distant galaxies stretches, increasing in wavelength. For Himiko, at a redshift of around Z6.6, this means that its ultraviolet and visible light, particularly its strong Lyman-alpha emission, arrives at Earth as infrared radiation. Ground-based observatories, while capable in many ways, are hindered by Earth's atmosphere, which absorbs large parts of the infrared spectrum and introduces noise from thermal emissions. That's where Spitzer and Hubble came in. Spitzer, launched in 2003, was specifically designed to peer into the infrared universe. With its cryogenically cooled instruments, it was able to detect heat signatures and faint light from some of the coldest and most distant objects ever studied. Himiko's redshifted emission fell perfectly within Spitzer's capabilities. When astronomers targeted Himiko with Spitzer's infrared array camera, IRAC, they found something striking: a powerful infrared source where the galaxy was thought to be. This confirmed that Himiko wasn't just an optical illusion or a trick of gravitational lensing. It was a real, energetic object pouring out radiation from deep time. Spitzer's data revealed the overall brightness of Himiko in multiple infrared bands, helping astronomers estimate the galaxy's stellar mass and star formation rate. Based on the flux measured by Spitzer, models suggested that Himiko could contain tens of billions of solar masses worth of stars, rivaling or even exceeding the mass of many modern dwarf galaxies. For such an early epoch, this was extraordinary. These mass estimates supported the idea that Himiko was a genuine giant among early galaxies, not just a compact burst of activity, but a sprawling, luminous structure. However, while Spitzer was sensitive to overall brightness, its resolution was limited. It could detect that light existed, but it couldn't sharply define how that light was distributed. That's where Hubble came in. Launched in 1990 and operating primarily in visible and ultraviolet light, Hubble revolutionized our view of the cosmos with its razor-sharp imaging. For Himiko, despite the galaxy's light being heavily redshifted, Hubble's longer wavelength filters, particularly in the near-infrared bands, were still able to detect the faint outlines of the galaxy's structure. What emerged was not a smooth elliptical blob or a clearly rotating spiral, but a chaotic, asymmetric layout, three distinct clumps of brightness, strung together like beads in space. These clumps, each hundreds to thousands of light-years across, appeared to be moving as a unit, embedded within a diffuse halo of light. This clumpy morphology shocked astronomers. Theoretically, galaxies in the early universe were expected to be small, irregular, and singular. Himiko was large, structured, and complex. The three bright knot feature raised the question: was Himiko one galaxy, or a merger of three smaller proto-galaxies in the process of coalescing? The answer wasn't immediately clear, but what was certain was that Himiko was not simple. It defied the neat categories into which early galaxies were supposed to fit. Hubble's ability to resolve these features was crucial not only for visualizing the galaxy, but for interpreting its history. The distribution of light helped astronomers model how stars were spread out, how concentrated the galaxy's energy output was, and whether regions of the galaxy were forming stars independently or as part of a shared system. Some of the clumps may have been undergoing their own mini-starbursts, while others appeared more diffuse. This diversity hinted at a galaxy in dynamic transition, caught in the act of assembling itself. Together, the data from Spitzer and Hubble offered a more complete picture. Spitzer gave the bulk properties, total brightness, stellar mass, and star formation rates, while Hubble provided the fine structure, the morphology, and the spatial context. The two telescopes, though fundamentally different in design and focus, acted as complementary tools. Without either one, our understanding of Himiko would be severely limited. Their synergy also enabled astronomers to identify emission lines and validate Himiko's redshift. By analyzing how much the light had stretched, they could calculate precisely when the light was emitted, placing Himiko in that critical epoch only 800 million years after the Big Bang. Confirming such an ancient origin wasn't trivial. High redshift galaxies are faint and elusive. Many candidates in deep surveys turn out to be contaminants, closer galaxies with unusual properties. But Spitzer and Hubble, by cross-validating the object's brightness and structure, made the case for Himiko's age and distance solid. Perhaps most importantly, the observations from these two telescopes cemented Himiko's role as an outlier. In massive deep-field surveys like the Subaru/XMM Newton Deep Survey and the Hubble Ultra Deep Field, Himiko stands out as one of the most luminous and spatially extended Lyman-alpha emitters in the early universe. Most galaxies observed from that era are faint smudges, tiny, low mass, and rapidly evolving. Himiko is a titan among them, and without the sharp eyes of Hubble and the deep infrared reach of Spitzer, we would have never known it. Even after the Spitzer mission ended in 2020, its data continues to be mined and cross-referenced. And with Hubble still operational, and the James Webb Space Telescope now joining the effort, Himiko is far from being forgotten. These telescopes represent the relay points in humanity's effort to see farther back in time, to detect not just the origins of galaxies, but the processes that shaped all large-scale structure. In Himiko, we see the legacy of these missions written in light. We see what becomes possible when we build instruments not just to look up, but to look deep, through time, through space, and into the mysteries that still lie untouched in the shadows of the early universe. In the vast, unlit corridors of early cosmic history, Himiko stands as a rare, glowing chamber, a cosmic laboratory frozen in time. It's not just a galaxy, it's a working model, a naturally occurring testbed where the universe's most fundamental processes are still visible in raw, unprocessed form. Every photon from Himiko that reaches our telescopes is more than a light signal. It's a data point, a piece of evidence that can help us test, refine, or even overturn our deepest assumptions about how the cosmos came to be. In Himiko's searing brightness, irregular structure, gas halo, and starbursting core, we find a crucible where the earliest blueprints of galaxy formation, dark matter structure, and cosmic evolution are still being sketched in real time. What makes Himiko such a powerful laboratory is its timing. It exists in a period known as the Epoch of Reionization, a transformative era that began a few 100 million years after the Big Bang and continued for several 100 million more. This was when the first stars and galaxies began emitting enough radiation to ionize the vast clouds of neutral hydrogen that filled the universe, turning the cosmos from a dark, opaque expanse into a transparent one. By existing within this narrow slice of time, roughly 800 million years after the Big Bang, Himiko offers scientists a direct window into how galaxies behave when the universe is still undergoing this fundamental phase change. In modeling the growth of early galaxies, cosmologists have developed large-scale simulations based on the principles of lambda cold dark matter, the standard model of cosmology. This framework assumes that the universe is composed primarily of dark energy and cold dark matter, with normal baryonic matter making up just a small fraction of the total. In these simulations, galaxies form hierarchically, small structures collapse first, then gradually merge to form larger ones. The process is expected to be slow and staggered, especially in the early universe. But Himiko doesn't behave like a galaxy that followed those slow steps. It appears too large, too luminous, and too active for its age. Its mere existence at such an early time challenges the standard assumptions of hierarchical structure formation. If galaxies are supposed to build up slowly from smaller clumps, how did Himiko manage to gather enough gas and form enough stars to become a sprawling, 55,000 light-year-wide object within just a few 100 million years? This question strikes at the heart of our theories. To understand whether Himiko is an exception or part of a broader, hidden population of massive early galaxies, astronomers use it as a benchmark case. They plug Himiko's properties, its size, star formation rate, gas content, and apparent structure, into computer simulations and see what initial conditions are required to recreate it. This helps refine our models of how matter cooled, condensed, and collapsed into galaxies after the Big Bang. For instance, it suggests that some regions of the early universe must have been unusually dense, allowing for faster-than-expected accumulation of mass. Himiko is also an invaluable tool for probing the elusive nature of dark matter. Though invisible, dark matter shapes the universe by exerting gravitational influence on visible matter. Galaxies like Himiko cannot hold themselves together without a massive underlying dark matter halo. There simply isn't enough visible mass to prevent them from flying apart under their own energy. By analyzing how the gas and stars in Himiko move and how the light is distributed, scientists can estimate the strength and shape of the gravitational well that contains them. If Himiko indeed resides in an enormous dark matter halo, it supports the idea that large-scale structure was already forming at cosmic dawn. But if the halo is less massive than expected, it could point toward alternative models of dark matter behavior, perhaps warmer, more interactive, or more complex than currently believed. The distribution of stars and gas in Himiko also feeds into theories of feedback and regulation in galaxy evolution. Most modern galaxies seem to go through cycles, bursts of star formation followed by quiescent phases, often regulated by feedback from supernovae or central black holes. But in Himiko's case, there's no evidence of a central AGN, and yet it is still producing stars at a breathtaking rate. That raises important questions. How long can a galaxy sustain such starburst activity without quenching itself? What internal or external forces might halt this growth? Does feedback play a lesser role in these early galaxies, or does it simply look different from what we see today? Then there's the issue of cosmic reionization. To reionize the universe, a large population of galaxies or other light sources must have emitted huge numbers of ionizing photons, far more than we observe today in the high redshift universe. Himiko, with its extreme brightness and low dust content, may be one of those rare galaxies that contributed disproportionately to the reionization effort. By studying its ultraviolet output and how it escapes into space, researchers can estimate how efficient such galaxies were at leaking ionizing radiation into the intergalactic medium. This, in turn, feeds back into large-scale models of how and when the fog of neutral hydrogen was finally lifted across the cosmos. On a more granular level, Himiko helps researchers test stellar population models and environments that are nearly pristine. Its stars likely formed from gas composed mostly of hydrogen and helium, with few heavy elements. This allows astrophysicists to study the spectral signatures of metal-poor or metal-free stars, improving our understanding of how the first generations of stars, possibly including population 3 stars, looked and behaved. Himiko may not contain population 3 stars directly, but it exists in the right timeframe and conditions to harbor their immediate descendants, giving scientists a rare chance to observe the aftermath of the first starlight. Moreover, because of Himiko's size and structure, it may even allow tests of gravitational lensing models and the effect of the intergalactic medium on light propagation. As Lyman-alpha photons scatter through space, they can be absorbed or redirected by clouds of neutral hydrogen, altering the observed shape and intensity of distant galaxies. By comparing Himiko's Lyman-alpha halo with theoretical expectations, astronomers can infer the density and composition of the cosmic medium it passed through on its way to us. In sum, Himiko is not just an ancient galaxy, it's a living equation etched into the cosmos, whose variables we are only beginning to understand. It is a test case for the age of light, a pressure point for cosmic theory, a challenge to the models we've spent decades refining. By analyzing its mass, light, gas, and environment, we calibrate our instruments not just for observation, but for comprehension. Each spectrum taken, each photometric point plotted, is another variable being tested in the universal formula we are trying to decode. And as we continue to push the limits of what our telescopes can see, now with the James Webb Space Telescope and soon with even more advanced tools, Himiko remains a standard against which the unknown can be measured. It is a rare gift, not just a relic of the past, but an active participant in the shaping of our scientific future. From the standpoint of our most trusted cosmological models, Himiko is a paradox that shouldn't exist. A sprawling, luminous galaxy, spanning over 55,000 light-years, roaring with star formation and glowing brightly in Lyman-alpha radiation, all within just 800 million years after the Big Bang. In a universe that was still largely dark and disorganized, this colossal structure appears as a fully formed beacon, defying expectations. According to standard theories, galaxies of such mass and complexity were not supposed to evolve so early. And yet, Himiko exists, clearly, brightly, and unignorably. Its presence is a cosmic contradiction, a challenge scrawled in starlight across the sky, forcing astronomers to revisit and revise their assumptions about how the first massive galaxies formed. The prevailing framework of structure formation is hierarchical. It suggests that the universe began as a relatively uniform sea of hydrogen and helium, with slight density fluctuations, imprinted during inflation, providing the seeds for future structure. Under the influence of gravity, these fluctuations grew. Small clumps of matter coalesced into the first dark matter halos, drawing in gas, forming stars, and eventually building up into dwarf galaxies. Over time, these dwarfs merged to form larger and more complex galaxies. In this view, the formation of massive galaxies was a slow, stepwise process, taking billions of years. The idea of a galaxy rivaling or exceeding the Milky Way's size existing less than 1 billion years after the Big Bang was almost unthinkable. And then came Himiko. Its discovery wasn't just a matter of surprise, it was a full-blown disruption. When astronomers first confirmed its size and luminosity, many initially questioned the data. Could it be a gravitational lensing artifact, where the light from a smaller object was magnified by a foreground mass? Could it be a chance alignment of multiple galaxies? But no. Observations from multiple instruments, including Subaru, Spitzer, and Hubble, confirmed it. Himiko is a single, massive, coherent system, existing at redshift c6.6, when the universe was less than 1 billion years old. Its size, brightness, and mass estimates were not errors, they were real. So why is this such a problem? To form a galaxy as massive as Himiko by this epoch, the universe would have needed to collapse matter far more efficiently than simulations predict. The cold gas required to fuel such rapid star formation would have had to flow into the galaxy without being disrupted or heated by the surrounding medium. It would also require that star formation ignite at high efficiency, converting gas to stars at a rate approaching theoretical limits. Not only that, but feedback from the stars themselves, especially from supernovae, would normally blow gas out of such a young galaxy, quenching further growth. Himiko seems to have sidestepped all of these barriers. Its star formation rate, likely around 100 solar masses per year, is well above what we would expect from early galaxies. Most others from the same epoch, those that have been studied in detail, form stars at a rate of 10 to 20 solar masses per year. Himiko is not just larger, it is more efficient, more intense, and more luminous. The lack of dust makes it easier to detect in certain wavelengths, but also points to a strange chemical simplicity for such a developed system, another clue that Himiko didn't follow the typical rules. This brings up the possibility that Himiko may have formed in a particularly rare and overdense region of the early universe. Such regions, where the density of matter was significantly higher than average, could have collapsed faster under gravity, leading to the rapid buildup of massive structures. These so-called protocluster environments may have been the cradles of the universe's first massive galaxies. If Himiko resides in such an area, it may not be alone. Other, fainter companions may orbit it, unseen until deeper observations can confirm their presence. Yet even this explanation doesn't fully resolve the issue. Cosmological simulations like Illustris, Eagle, and others based on lambda cold dark matter models have struggled to produce analogues to Himiko without pushing the parameters to extremes. Either the dark matter halos must collapse earlier than expected, or the efficiency of gas cooling and star formation must be unnaturally high. In some scenarios, astrophysicists have had to invoke non-standard physics, such as modified dark matter behavior or variations in the initial mass function of stars, to explain galaxies like Himiko. There's also the speculative but intriguing idea that galaxies like Himiko may have formed from the direct collapse of massive gas clouds, bypassing the need for multiple mergers. Instead of building up from small parts, a single, large reservoir of pristine hydrogen could have collapsed into a massive galaxy almost all at once, triggered by unknown mechanisms. This would allow rapid formation on short timescales, but such events would be rare and require very specific environmental conditions. Himiko might be one of these rare, monolithic collapse objects, cosmic flukes that represent an alternative pathway to galaxy formation. Another possibility is that our understanding of feedback in the early universe is incomplete. Perhaps feedback from supernovae and stellar winds didn't inhibit star formation as much as previously thought. If early galaxies were more resistant to disruption, or if their gravitational wells were deeper due to massive dark matter halos, then sustained star formation at extreme rates might have been more common than models currently assume. But even as astronomers explore these theories, one thing is clear: Himiko is forcing change. It is compelling theorists to revisit assumptions about gas accretion, cooling timescales, starburst triggers, feedback regulation, and the very timing of large-scale structure formation. Every data point pulled from this galaxy adds pressure on simulations to match what we see, not just in aggregate, but in detail, at specific cosmic times. And that pressure is growing. Himiko is not entirely alone. With telescopes like JWST now scanning the deep universe with unprecedented sensitivity, other massive early galaxies are beginning to appear. Each one adds weight to the case that our models of early galaxy formation are missing something critical, something Himiko was already trying to tell us years ago. So yes, Himiko shouldn't exist. Not by the rules we've written. Not by the growth curves and feedback loops and slow hierarchies we've trusted for decades. And yet, here it is. A sprawling furnace of stars from the first billion years of time, a cosmic contradiction that quietly mocks our models with its luminous defiance. The question is no longer, how did this happen? It's now, what else have we misunderstood? One of the most fascinating puzzles surrounding Himiko is not just how it became so large, so bright, and so active, but how it may have done so in isolation. Galaxies, especially in the early universe, are generally thought to grow through frequent interactions and mergers. They live in a cosmic web, connected by filaments of gas and dark matter, constantly influenced by gravitational tugs and exchanges of material. But Himiko, based on current observations, seems to sit alone. No obvious galactic neighbors, no tidal tails, no clear signs of a dense galactic environment. This solitude only deepens the mystery of its existence. Because if Himiko is indeed forming stars at an astonishing rate without companions, then the assumptions about early cosmic structure might need a serious revision. To be clear, the notion that Himiko is forming stars in isolation doesn't mean it was born in a cosmic void. Rather, it means that in its immediate observable vicinity, there are no other major galaxies visible that are interacting with it or contributing significant matter through mergers. This is especially perplexing considering Himiko's scale. At over 55,000 light-years across, it's not just big for its time, it's comparable in size to modern galaxies that took billions of years to assemble. That kind of mass, that level of star formation, and that structure are usually tied to regions where galaxies are densely packed together, often within early forming clusters or protoclusters. But Himiko isn't sitting in a swarm of galaxies. It appears to be glowing alone. This has profound implications. For starters, it suggests that the universe's large-scale structure, the intricate web of filaments, voids, and nodes that now defines cosmic geography, may not have been as fully developed or connected as previously thought during Himiko's era. If galaxies like Himiko can grow massive and bright far from major hubs of activity, it means that the formation of large galaxies may not have been exclusively tied to densest nodes of matter. Gravitational collapse may have been more chaotic or asymmetric, allowing some massive galaxies to emerge earlier and in more isolated regions than expected. Alternatively, it might be that the environment around Himiko is more crowded than it looks, but the other galaxies are too faint to detect with current instruments. If its surroundings are populated by low-mass, dim galaxies, they might be below the detection threshold even for telescopes like Hubble or Spitzer. They could still be contributing gas or material gravitationally, or influencing Himiko's structure in subtle ways. The James Webb Space Telescope may eventually detect these fainter companions and fill in the map around Himiko, revealing whether it's truly isolated or merely surrounded by invisible players. But if it is truly alone, that opens up another possibility, one where Himiko pulled in mass directly from the intergalactic medium. This scenario, known as cold gas accretion, involves vast rivers of pristine hydrogen flowing along filaments of the cosmic web and collapsing directly into the galaxy's gravitational well, skipping the usual merging pathway. If Himiko had access to an unusually straight, uninterrupted supply of cold gas, it could have fueled its rapid starburst growth without needing help from nearby galaxies. This would make Himiko a rare demonstration of monolithic collapse, a model of galaxy formation that is generally considered outdated but may still apply in certain early universe extremes. The implication of isolated star formation also touches on the formation of galactic structure without major disruptions. In dense environments, galaxies tend to be pulled, stretched, and distorted by their neighbors. Tidal interactions and mergers scramble their morphology. But Himiko, while irregular, does not show the violent asymmetries or torn-apart shapes typically associated with such interactions. Its three bright clumps appear relatively stable, and its extended Lyman-alpha halo is smooth and coherent. If Himiko formed largely undisturbed, it might offer a cleaner example of early star formation than galaxies shaped by constant mergers. Yet even that assumption has its limits. The apparent tranquility of Himiko's surroundings may be deceiving. It's possible that Himiko underwent a massive merger in the very recent cosmic past, and we are catching it just after the merger has completed. In this scenario, the merging galaxies have coalesced quickly, and the tidal features have already faded or become indistinct due to the immense gravitational binding and energy dissipation. This would preserve Himiko's smooth outer glow while explaining its sudden size and activity. But again, the lack of observable companion galaxies or debris remains a sticking point. More speculative still is the idea that Himiko formed in a region of biased initial conditions, a small segment of the early universe where the matter density, velocity fields, and gas temperatures all conspired to create an exceptional outlier. It may be that we are witnessing the product of a very rare pocket of conditions, a kind of early universe, sweet spot, where isolation didn't hinder development but enhanced it. These pockets may be statistically inevitable in a universe as vast and chaotic as ours, but their discovery can radically shift our sense of what's probable versus what's possible. Isolation, or apparent isolation, also affects the kinds of stars Himiko may have produced. In denser regions, heavy element enrichment happens faster. Supernovae from one galaxy can seed nearby galaxies with metals. But if Himiko is cut off from other systems, it may have formed stars from more pristine, low metallicity gas, closer to the compositions of the universe's earliest materials. This could affect not only the efficiency of star formation, but also the mass distribution of stars, the formation of stellar clusters, and the development of complex chemistry necessary for later planetary systems. So what is Himiko teaching us here? At the very least, it reminds us that massive galactic evolution is not always a team sport. Under the right conditions we still don't fully understand, galaxies can rise from the cosmic voids themselves, pulling in gas, forming stars, and blazing across the sky without the need for immediate neighbors. Himiko, in its apparent solitude, is not silent. It's speaking volumes about how the early universe might have nurtured giants not through crowding, but through the quiet, unimpeded flow of matter and time. If it truly formed stars in isolation, then our search for early galaxies must widen. We must look not only in dense cosmic nurseries, but also in the dark stretches between them. Himiko may not be alone in its loneliness, and in that possibility lies an entire new frontier of discovery. To fully appreciate the ancient nature of Himiko, one must look beyond its sheer size or brightness and delve into the elemental composition of the universe at the time it formed. Himiko emerged during an era when the cosmos was still chemically young, a time before heavy elements. The universe, in its infancy, was dominated almost entirely by the two lightest elements, hydrogen and helium. These primordial gases were forged in the first few minutes after the Big Bang through a process known as Big Bang nucleosynthesis, and they comprised nearly the entirety of all matter for hundreds of millions of years. Elements heavier than helium, known as metals in astronomical terms, didn't yet exist in significant quantities. They had to be created inside stars, and in the time of Himiko, the stars had only just begun to blaze. Himiko, being visible just 800 million years after the Big Bang, likely formed from this pristine, or near-pristine material. That means the stars within it, especially the earliest generations, were composed almost entirely of hydrogen and helium, without significant traces of carbon, oxygen, iron, or other heavier elements. This has profound implications for how those stars would have formed, evolved, and died, and it gives astronomers a chance to study conditions that no longer naturally occur in the present-day universe. In the absence of metals, star formation behaves differently. Heavy elements play a crucial role in cooling gas clouds, allowing them to collapse more efficiently under gravity. Without these metals, gas cools less efficiently, which typically leads to the formation of much more massive stars than what we see in our contemporary stellar neighborhoods. These stars, hypothesized to belong to the fabled population 3 class, may have reached masses hundreds of times that of the Sun and would have lived short, luminous lives before exploding as supernovae, or even collapsing directly into black holes. Himiko may not be home to population 3 stars directly. Those may have already lived and died by the time Himiko was fully formed, but the galaxy likely bears the imprint of their influence. The heavy elements we do observe in galaxies like Himiko must have come from these first, short-lived generations of stars. This means Himiko occupies a chemical transition point in the universe's history, a bridge between a time when stars were forged only from hydrogen and helium, and a later era when the cosmos began to teem with elements essential for planets, atmospheres, and eventually life. Spectroscopic data from Himiko reveals very low metal content, which is consistent with this picture. The Lyman-alpha emission that makes Himiko so prominent is less likely to be absorbed or scattered by dust and metals in such an environment, helping it shine even more brightly. But this lack of metals also reinforces just how early in cosmic time Himiko appeared. It is one of the few known galaxies where astronomers can study star formation in an environment that is only 1 or 2 steps removed from the raw, primordial state of the universe. The consequences of this extend far beyond just understanding Himiko itself. By analyzing the metallicity of Himiko and galaxies like it, astronomers can trace the history of chemical enrichment in the cosmos. They can measure how quickly elements like carbon, nitrogen, and oxygen began to accumulate after the first stars formed. This, in turn, feeds into models of when the conditions for planetary systems and eventually life could have emerged. Because without metals, there can be no rocky planets, no Earths, no carbon-based life forms. The story of Himiko, then, is also the story of the chemical roots of our own existence. Another intriguing implication of the low metallicity environment is how it might affect stellar feedback. The process by which radiation, stellar winds, and supernovae influence the surrounding interstellar medium. Stars formed in such metal-poor conditions may have exploded with greater force, or radiated more intensely, injecting enormous amounts of energy into their environment. This could have helped blow out gas, regulate star formation, or even contribute to the reionization of the universe. In this way, the composition of the stars themselves influenced the evolution of the galaxy as a whole, creating a feedback loop that shaped its fate. And yet, despite the limited metals, Himiko shines with remarkable intensity. This suggests that metal-rich environments are not a prerequisite for extreme luminosity in early galaxies. Instead, it may be that the abundance of pristine gas, combined with high-efficiency collapse mechanisms, drove Himiko's starburst behavior. It raises fascinating questions about how long such metal-poor galaxies could sustain this level of activity, and whether they transitioned quickly into more chemically complex systems, or burned out rapidly, leaving behind a chemically evolved remnant. Looking ahead, galaxies like Himiko are prime targets for next-generation spectroscopic studies. Instruments on the James Webb Space Telescope are already being used to peer into their elemental fingerprints, measuring not just the presence of metals, but the ratios between them. These ratios act like time capsules, revealing the kinds of stars that contributed to the enrichment, how fast they evolved, and what mechanisms governed their life cycles. From the relative abundance of oxygen to neon to iron, researchers can reconstruct a chemical timeline of the galaxy's growth. In this way, Himiko is more than an ancient galaxy. It's a chapter from the universe's early chemistry book, opened for the first time in eons. It allows us to study a version of the cosmos where everything was new, raw, and untouched by the cycles of stellar death and rebirth that now saturate our local universe. Through its light, we glimpse a cosmos before complexity, before planets, before biology, before even the seeds of what we would eventually call civilization. In that glow, forged from hydrogen and helium, lies the untouched handwriting of the universe's first elements. Peering into the depths of space is like looking through a time machine, and galaxies like Himiko provide one of the clearest windows into the universe's first billion years. During that epoch, the cosmos was undergoing one of the most profound transformations in its entire history. The first stars had ignited, their intense radiation breaking the long silence of the cosmic dark ages. Galaxies were just beginning to assemble, light was piercing through the fog of neutral hydrogen, and the cosmic web was knitting itself into the vast structure we see today. Himiko is not just a relic from that time, it is a living photograph, a snapshot capturing a moment in the universe's adolescence, when order was emerging from chaos, and complexity was just taking root. To understand the importance of this glimpse, it helps to consider how staggeringly little we actually know about the universe in its first billion years. The earliest few 100,000 years are well charted thanks to the cosmic microwave background, a relic glow that maps the infant universe with exquisite precision. Billions of years later, the modern universe is accessible in countless wavelengths, its galaxies, clusters, and large-scale structures studied in detail. But between those two extremes, the blank middle chapters, lie the greatest cosmic mysteries. This is the Epoch of Reionization, the shadowy transitional phase when the first light sources emerged and began to sculpt the universe into what it is today. Himiko formed during this twilight, when the cosmic fog was just beginning to lift. Its very visibility is a sign that the universe was becoming more transparent, because before this time, even the most luminous objects were veiled by neutral hydrogen, which readily absorbed ultraviolet light. But galaxies like Himiko shine through. They blaze brightly enough to be seen across nearly 13 billion light-years of space, revealing that at least some parts of the early universe were already clear enough for light to travel unimpeded. Observing them allows astronomers to map the progress of reionization, to see which regions of the universe had been cleared of the hydrogen mist, and which remained opaque. And yet, such galaxies are incredibly rare. Despite deep field surveys, thousands of hours of exposure time, and the full attention of some of humanity's most advanced instruments, only a handful of objects from this early period have been discovered that rival Himiko in size and luminosity. Most galaxies detected at these redshifts are small, faint, and hard to characterize. Himiko, with its immense brightness and extended structure, is an outlier, a golden find. It gives us an extraordinary opportunity to study the mechanisms of early galaxy formation, and to do so with a level of clarity usually reserved for much more recent epochs. What makes Himiko particularly valuable is that it bridges two epochs. It appears at the end of the Dark Ages and at the beginning of the era of widespread galactic growth. This puts it in a perfect position to help answer fundamental questions. How quickly did galaxies form after the first stars ignited? What did the earliest starburst regions look like? How did galaxies begin to cluster, evolve, and shape their surroundings? Himiko provides direct observational evidence, anchoring theoretical models in something real and tangible. It also tells us something crucial about the speed of cosmic evolution. The fact that a galaxy like Himiko had already assembled so much mass, organized itself into a multi-clump structure, and begun to form stars at such a breakneck pace, all within 800 million years, suggests that the early universe was capable of accelerated development. That contradicts older assumptions which painted the first billion years as a slow, tentative emergence of structure. Himiko's presence argues instead for vigorous and rapid cosmic engineering, a universe where complexity was not only possible but happening fast. These glimpses are not just informative, they are transformative. Every observation of a galaxy like Himiko rewrites part of the cosmic timeline. It forces theorists to update simulations, to rework models of gravitational collapse, cooling, feedback, and structure formation. Without galaxies like Himiko, we would be left guessing about how the primordial gas collapsed into the luminous architecture we see today. With it, we have a beacon, shining backward through time, illuminating the path from simplicity to structure. The first billion years also mark the time when the rules of modern cosmology were written. Dark matter began to clump in meaningful ways. The first black holes likely formed, perhaps some of them seeds that would grow into the monsters at the centers of today's galaxies. Elements heavier than helium, carbon, oxygen, nitrogen, began to enrich the interstellar medium. Stars started to live and die in cycles, feeding new generations with their ashes. Himiko is not just a fossil from this age, it is part of the machinery that made all of that happen. As such, it represents more than a moment in cosmic history, it's a tool for decoding it. Its characteristics, mass, luminosity, structure, metallicity, and radiation profile, each serve as data points, guideposts pointing toward the underlying physics that govern the birth of galaxies. And with the help of advanced instruments like the James Webb Space Telescope, we're now peeling back even more layers, resolving features in Himiko and other early galaxies with unprecedented resolution. These observations are already helping to test the limits of our theories, from dark matter behavior to the nature of the very first stars. In the end, Himiko is more than a galaxy, it's a story written in light, traveling for over 13 billion years to reach us. It tells of a universe that was not quiet or empty, but dynamic, creative, and full of surprises. In its sprawling clumps and glowing halo, we see the fingerprints of a cosmos just beginning to awaken, to form stars, galaxies, and the elements that would one day become life. It is a glimpse into the first billion years, fleeting, fragile, and fiercely bright. The discovery of Himiko was already extraordinary, but it was spectroscopy that transformed this luminous smudge on a detector into one of the most important pieces of evidence in our understanding of the early universe. It was through spectroscopic breakthroughs that astronomers were able to pin down its astonishing distance, and by extension, its age, by confirming its redshift at approximately Z6.6. This places Himiko not only far in space, but deep in time. What we see is light that has been traveling for 12.9 billion years, meaning we're observing the galaxy as it was when the universe was only about 800 million years old, just 6% of its current age. This redshift confirmation is crucial. Without it, we could only guess at Himiko's distance based on photometric estimates, broadband color data that can sometimes mimic high redshift signals due to dust or other contaminants. But spectroscopy offers certainty. When astronomers dispersed Himiko's light into a spectrum, they found an unmistakable signature, a sharp Lyman-alpha emission line, redshifted from its original ultraviolet wavelength to much longer wavelengths due to the expansion of the universe. This single feature anchored Himiko in cosmic history, fixing it in one of the earliest chapters of galactic evolution ever observed. The process of getting this spectrum was not trivial. Galaxies at Z6.6 are incredibly faint and difficult to isolate from the noisy background of the sky. The light from such distant objects is stretched so much by cosmic expansion that it falls into the infrared portion of the spectrum, requiring highly sensitive detectors and long exposure times. Observations of Himiko were carried out using some of the world's most powerful tools, including the Spitzer telescope in Hawaii, which provided the initial detection, and later instruments like the Spitzer Space Telescope and the Hubble Space Telescope, which helped refine its photometric profile and guided spectroscopic targeting. What astronomers were looking for, and found, was the Lyman-alpha line, a spectral signature emitted when electrons and hydrogen atoms drop from the second energy level to the first, releasing energy in the form of ultraviolet light. At Himiko's redshift, this line has been stretched to around 9,200 angstroms in the near-infrared, where only a few instruments are sensitive enough to detect it. And detect it they did, not just as a faint trace, but as a strong, well-defined emission line, confirming that Himiko is not a foreground object, not a contaminant, but a genuine beacon from the early universe. This confirmation did more than just verify Himiko's age. It also opened the door to studying the properties of its interstellar and intergalactic environments. The shape and strength of the Lyman-alpha line carry important information. For example, a sharp, asymmetric profile with a red tail can suggest outflowing gas, indicating active star formation and possibly galactic winds. It also tells us about the opacity of the intergalactic medium, IgM, at the time. Since Lyman-alpha photons are easily absorbed by neutral hydrogen, the fact that Himiko's signal is detectable at all implies that it exists in a region of the universe that had already undergone significant reionization, where hydrogen was being ionized by ultraviolet radiation. But spectroscopy did more than measure redshift. It also helped place constraints on the galaxy's stellar population, star formation rate, and dust content. By analyzing the continuum light in the near-infrared, astronomers could estimate the ages of the stars, their metallicities, and the amount of extinction caused by dust. In Himiko's case, the spectrum showed a surprisingly smooth continuum, suggesting a dominant population of young, hot stars and very low levels of dust, a clue that Himiko had not yet undergone the multiple cycles of star birth and death that tend to enrich galaxies with heavier elements and interstellar particles. Later spectroscopic follow-ups attempted to detect other emission lines, such as those from oxygen, O3, or carbon, C2, which would allow more precise measurements of metallicity and ionization states. In Himiko's case, these lines have proven elusive or faint, reinforcing the idea that this galaxy is extremely metal-poor, likely still in a chemically primitive state. This aligns with theoretical expectations for a galaxy that formed so early, when heavy elements had not yet had time to accumulate. The redshift determination also provided a calibration point for cosmological models. At Z6.6, the universe was in a unique phase, still transitioning from the Dark Ages into the Epoch of Reionization. By confirming that a massive, luminous galaxy like Himiko existed at this redshift, theorists were forced to reconsider the speed at which large-scale structures could emerge. It added another data point to the timeline of cosmic evolution, a signal that complexity had arrived earlier and more intensely than expected. And with this spectroscopic anchor in place, astronomers began to search for more galaxies like Himiko. Knowing its redshift allowed them to design filters and instruments specifically tuned to catch similar objects, Lyman-alpha emitters and Lyman break galaxies, at comparable distances. Himiko became a template for discovery, a kind of early universe Rosetta Stone helping decode the language of cosmic infancy. Looking forward, spectroscopy remains the key to unlocking even deeper truths about Himiko and its peers. The James Webb Space Telescope, with its unparalleled infrared sensitivity and high-resolution spectrographs, is already opening a new window into this era. JWST's instruments can detect not just the basic emission lines, but the faint continuum spectra of individual stellar populations, the fine structure lines of carbon and oxygen, and the warm dust signatures that trace star-forming regions in exquisite detail. For Himiko, this means we will soon be able to measure its internal dynamics, estimate the masses of its clumps, map the motion of gas, and perhaps even detect the echoes of its earliest supernovae. But it all began with that one breakthrough, the identification of the redshifted Lyman-alpha line at Z6.6. That single feature, carved into the spectrum by the ancient hydrogen atoms of a galaxy long gone, told us exactly when and where Himiko lived. It transformed a mysterious blob into a cornerstone of early universe astronomy, forever placing it among the most important celestial finds of our time. Himiko doesn't resemble the serene, symmetrical galaxies we often see in images of the modern universe. It lacks the graceful spiral arms of the Milky Way, the central bar of galaxies like NGC 1300, or the smooth, spherical halos that mark evolved elliptical galaxies. In fact, Himiko doesn't appear to be settled at all. It is, instead, raw, chaotic, clumpy, and primitive. The absence of the features we associate with galactic maturity is not a flaw or a mystery, but rather a vivid sign of its youth. Himiko is a galaxy in its infant state, caught in the act of assembling itself in a universe still fresh from its explosive birth. This structural simplicity, or rather, structural turbulence, is exactly what one would expect from a galaxy born just 800 million years after the Big Bang. The universe at that time was still a violent place, filled with collapsing gas clouds, fast-moving matter, and the harsh radiation of newly ignited stars. The dark matter scaffolding that would eventually guide the smooth formation of galaxies was still settling into place. Gravity was pulling gas into clumps, but those clumps had not yet settled into the elegant, rotating disks we associate with spirals. Himiko, with its 3 bright regions of star formation, shows no sign of a unified rotational symmetry. It isn't spinning in a defined direction or following any smooth orbital dynamics. It's more like a cosmic construction site, where the foundation has been poured, the beams are in place, but the structure is far from complete. The lack of a central bulge or core is another key difference from modern galaxies. In more evolved systems, there's often a dense, compact region at the center, sometimes housing a supermassive black hole, and typically rich in older stars. This central bulge can dominate the dynamics of the galaxy, anchoring its rotation and shaping the orbits of stars around it. Himiko, by contrast, doesn't show any indication of such a core. Its light is not concentrated toward the center, and there's no spectroscopic signature of a strong gravitational source dominating the galaxy's heart. Instead, the 3 distinct clumps suggest a distributed star-forming architecture, possibly indicative of multiple subgalaxies in the process of merging. This clumpy, irregular morphology is an essential clue to how galaxies grow. The smooth disks and bulges of modern galaxies are the end results of billions of years of mergers, interactions, and internal evolution. Early on, galaxies likely formed in fragments, localized bursts of star formation occurring in dense pockets of gas. These clumps, over time, would be drawn together by gravity, colliding and coalescing into larger structures. Himiko represents a snapshot of that process in action. It is not one galaxy, in the classical sense, but a dynamic network of forming components, each burning brightly with newly born stars, yet not yet unified into a singular shape. What's also striking is the absence of large-scale structure. In more mature galaxies, we see clearly defined arms, spiral density waves, rings, bars, and even warps that suggest the influence of both internal dynamics and external gravitational interactions. In Himiko, none of these are present. The edges of the galaxy are undefined and diffuse, with extended gas halos glowing in Lyman-alpha light. There is no sense of symmetry or balance, only a brilliant but turbulent mess of radiation and matter. In many ways, it resembles simulations of galaxy formation more than the galaxies we see in the night sky today. This makes Himiko incredibly valuable for astrophysics. Because it is so unlike modern galaxies, it provides a benchmark for how galaxies looked before they stabilized, before they fell into ordered rotation or began recycling gas through well-regulated feedback loops. It shows us that the early universe was not filled with elegant spirals or majestic ellipticals, but with anarchic, rapidly evolving blobs of gas and stars, each on a different path toward becoming something more recognizable. Its chaotic appearance also points to the lack of strong galactic organization mechanisms. For instance, the influence of a central supermassive black hole can help regulate star formation and shape the structure of a galaxy through feedback processes, such as jets and radiation-driven outflows. But with no strong evidence of such a black hole in Himiko, there's nothing enforcing symmetry or suppressing runaway star formation. The result is an unfiltered burst of cosmic activity, painting the galaxy in uneven brightness and undefined form. Another important factor is the galaxy's gravitational maturity. Modern galaxies have deep gravitational wells that help them retain gas, stars, and dust, which in turn allows them to regulate growth and evolve in relatively smooth stages. Himiko may not have such a deep well yet. Its gravitational potential is likely still being shaped by mergers and mass accretion. This means gas can escape more easily, star formation can be wildly uneven, and the structure can remain irregular for long periods. The lack of symmetry is a sign that gravitational equilibrium has not yet been achieved. Himiko is still in flux, still evolving, still finding its cosmic identity. This primitive nature extends to the internal dynamics as well. Without ordered rotation or settled orbits, the motions of stars and gas in Himiko are likely random, chaotic, and multidirectional. This kind of motion leads to turbulent star-forming environments, where gas clouds collide and collapse with little predictability, fueling rapid and perhaps short-lived episodes of starburst activity. It's not an efficient or stable mode of star formation, but it gets the job done, and fast. Himiko's intense brightness and high star formation rate suggest that despite the chaos, it's incredibly productive. So, while Himiko may not have the elegance or composure of a modern galaxy, it's all the more fascinating for it. Its raw, chaotic, and primitive appearance is not a flaw, it is a window into a time before order. It's a chance to observe the universe when everything was still under construction, when the first galaxies were more like flickering fires in the dark than the grand cosmic cities we see today. In its clumpiness and lack of defined form, Himiko reveals the story of how galaxies are born, not as polished structures, but as roiling, luminous clouds clawing their way toward coherence. Long before the modern universe filled with transparent space and visible starlight, there was a time when light struggled to travel freely, a time when the cosmos was veiled in darkness. This was the era of cosmic opacity, a period defined by the dominance of neutral hydrogen. And Himiko, blazing fiercely from that primordial night, shines as a rare exception, a bright signal piercing through the fog. To understand why Himiko's visibility is so remarkable, we must dive into the nature of the universe shortly after the Big Bang, and the slow process that transformed the lightless void into the radiant universe we see today. After the Big Bang, the universe expanded and cooled. At around 380,000 years old, it became cool enough for protons and electrons to combine into neutral hydrogen atoms, a phase known as recombination. This event released the cosmic microwave background, CMB, and marked the beginning of the so-called cosmic dark ages. For the next several hundred million years, there were no stars, no galaxies, and no luminous structures, only cold, neutral gas stretching across space, uniformly blanketing the universe in a dark, invisible shroud. Neutral hydrogen is highly effective at absorbing ultraviolet, UV, radiation, particularly at the wavelengths of Lyman series transitions such as Lyman-alpha, which is emitted when electrons and hydrogen atoms drop from the second to the first energy level. This means that during this dark age, any photons emitted by the first luminous objects would likely be absorbed or scattered almost immediately, never making it far through the intergalactic medium. The entire cosmos was, essentially, opaque to light, with vast clouds of neutral hydrogen acting like a cosmic fog. So how is it that we can see Himiko at all? The answer lies in the transformative period known as the Epoch of Reionization. As the first stars and galaxies formed, they began to emit enormous amounts of high-energy ultraviolet radiation. This radiation had enough energy to ionize neutral hydrogen, breaking it back into free protons and electrons. Slowly, over hundreds of millions of years, ionized bubbles began to form around these early light sources. These bubbles grew, overlapped, and eventually merged, clearing the neutral hydrogen from vast regions of space. As this reionization progressed, more and more light could travel unhindered across the universe, allowing galaxies to become visible to observers billions of years later. Himiko shines through this complicated backdrop. At redshift c6.6, it existed when the universe was still undergoing reionization. The process was not yet complete. Large portions of space were still saturated with neutral hydrogen, which should have absorbed or scattered Himiko's light. And yet it reaches us. That fact alone tells us something powerful. Himiko must reside within or near a reionized bubble, a cleared-out region where light could escape. Either it created this bubble on its own, through its intense star formation and ultraviolet output, or it benefited from reionization efforts by neighboring galaxies, even ones we haven't yet observed. If Himiko helped ionize its local environment, the implications are profound. It would mean that it is not just a product of reionization, it is one of the agents responsible for causing it. Galaxies like Himiko may have played a critical role in reionizing the universe, one patch at a time. With its high star formation rate, possibly around 100 solar masses per year, it could have generated enough UV radiation to carve out a significant transparent region, allowing its Lyman-alpha photons to travel across space and time, ultimately reaching our telescopes nearly 13 billion years later. But the picture is still more complex. The presence of a visible Lyman-alpha line in Himiko's spectrum, despite the surrounding opacity, suggests that reionization was patchy. It wasn't a uniform, gradual fog lifting, it was more like a series of holes being punched into a dense veil. Some areas cleared out quickly, while others remained neutral for much longer. Himiko likely sits within one of these cleared regions, either as a lone ionizer or as part of a small cluster of early galaxies all contributing to the local reionization bubble. There's also the intriguing possibility that the shape of the galaxy itself influenced its visibility. Lyman-alpha photons are resonantly scattered, meaning they interact heavily with hydrogen atoms. If Himiko's internal structure or outflows allowed these photons to shift slightly in wavelength before escaping, they might have redshifted just enough to avoid absorption by the neutral hydrogen outside. This mechanism, known as Lyman-alpha line offset, could allow galaxies like Himiko to shine even in partially neutral surroundings, helping to explain how we can see them at all. Still, the fact remains, most galaxies from Himiko's era are too faint or too obscured to detect. Himiko is the exception, not the rule. Its brightness, combined with its fortunate location within or near a reionized bubble, makes it one of the very few windows we have into a time when light was struggling to break free. Each Lyman-alpha photon that reaches us carries a tale of resistance, against the pull of gravity, the drag of gas, the scattering of dust, and above all, the dense hydrogen that once filled the void. This is why Himiko is such a precious find. It doesn't just reveal what an early galaxy looked like, it illuminates the universe's transition from darkness to light. It proves that even when the universe was largely opaque, there were already regions of clarity, beacons of light punching through the dark. And each of those beacons tells us something about the process of cosmic transformation, about how energy, matter, and radiation began to interact in new ways to reshape the very structure of space. We are now using galaxies like Himiko to map the timeline of reionization. By studying when and where these galaxies appear, and how their light interacts with the surrounding medium, we can determine how long the universe remained opaque, how fast reionization progressed, and what kinds of galaxies contributed to it. In this sense, Himiko is both a subject of study and a tool for discovery, helping us chart the path from invisibility to illumination. And so, Himiko shines not just across space, but across time. It reminds us that even in the deepest darkness, light finds a way, not because it is allowed, but because it insists. Against the opacity of the early universe, Himiko blazed forward, carving a visible path through the ancient fog, leaving behind a message that would take nearly 13 billion years to arrive. Himiko's presence in the early universe is not just impressive, it's statistically astonishing. At a time when most galaxies were faint, compact, and just beginning to form, Himiko emerged as a colossal anomaly, vast in size, stunningly luminous, and wildly active. It is, without exaggeration, a rare cosmic beacon, standing out in the sparse landscape of the young cosmos like a lighthouse in a black sea. Its discovery defied expectations, and even now, years after it was first observed, it continues to be an outlier, both in terms of its physical properties and its very existence. Galaxies from the Epoch of Reionization, roughly 400 to 800 million years after the Big Bang, are notoriously difficult to find. They are extremely distant, their light stretched to infrared wavelengths, and typically low in luminosity, with only modest star formation rates and limited structure. These galaxies, the building blocks of modern-day giants, are expected to be small, irregular, and dust-poor. Most are so faint that even with the combined power of the Hubble Space Telescope and Spitzer, they appear as tiny smudges at the edge of detection. Many are identified statistically, inferred from dropouts and multi-wavelength surveys, but not directly observed in great detail. And then, there's Himiko. Discovered in a wide-field survey using the Subaru telescope, Himiko's brightness was immediately puzzling. It didn't just stand out, it radiated with an intensity comparable to galaxies formed billions of years later. Its strong Lyman-alpha emission, immense size, approximately 55,000 light-years across, and high star formation rate made it utterly unique. Even after deeper surveys and years of technological advancement, few, if any, galaxies from that era rival Himiko in both size and luminosity. It remains one of the brightest Lyman-alpha emitters ever detected at such a high redshift. This rarity is part of what makes Himiko so scientifically valuable. Because there are so few like it, each one becomes a case study in early cosmic evolution. Himiko offers clues about the upper limits of galaxy formation during the universe's first billion years. How massive could galaxies get in such a short time? How much gas could they collect, cool, and convert into stars? Himiko shows us that even under what we thought were extreme constraints, nature found a way to break the rules. The sheer improbability of finding a galaxy like Himiko so early also forces astronomers to question their assumptions. Was Himiko just lucky, the product of a rare combination of factors that allowed for rapid growth and high luminosity? Or are there more galaxies like it, hidden from view by dust, or beyond the sensitivity limits of our instruments? If Himiko is not unique but merely the tip of a cosmic iceberg, then we may be underestimating the early universe's capacity for complexity and structure. It also raises important questions about the role of dark matter and the initial conditions of galaxy formation. Did Himiko form within a particularly massive dark matter halo? Was it seeded by an unusually dense region of primordial gas? Did it benefit from early mergers, rapidly assembling mass in ways that other galaxies could not? These questions are not just academic. They go to the heart of how the universe evolved from uniformity to the richly structured web of galaxies, clusters, and superclusters we see today. Furthermore, its luminosity gives Himiko exceptional reach. Because it's so bright, it can be studied in greater detail than most galaxies at its redshift. Astronomers can analyze its spectral features, examine its structure, and model its internal processes in ways that are impossible for fainter objects. Himiko, in this sense, is like a magnifying glass into the distant past, allowing us to infer the behavior of galaxies that are too faint to see directly by studying a luminous counterpart in exquisite detail. Even with the James Webb Space Telescope now active, capable of detecting far fainter galaxies than Hubble or Spitzer, Himiko retains its position as an upper-bound anomaly. It sets a benchmark. Any newly discovered early universe galaxy that comes close to matching Himiko's brightness, mass, or size is immediately measured against it. And still, the list of challengers remains short. Himiko is a statistical outlier, a rare occurrence in the cosmic population, which only increases its value. But rarity in astronomy often hints at something profound. Objects like Himiko, rare, brilliant, and hard to explain, tend to carry lessons that go beyond themselves. They force the scientific community to refine simulations, to stretch theoretical models, and to reconsider what is possible under extreme conditions. They highlight the diversity of the early cosmos, showing that even when the average galaxy was small and dim, exceptions were blazing into existence with astonishing vigor. It is these rare cosmic beacons that redefine the boundaries of knowledge. They stand as evidence that the universe is often more creative, more chaotic, and more capable of surprises than our most sophisticated equations allow. Himiko, with its powerful glow and improbable profile, is one such surprise. It teaches us not only about itself, but about the rules it appears to break, rules that, when rewritten, help us better understand how everything else came to be. In a universe governed by statistical norms, Himiko is the glorious exception. And exceptions, in science, are often the most revealing truths of all. Though we can't see it, can't touch it, and can't directly detect it, dark matter is thought to be the backbone of every galaxy in the universe, and Himiko is no exception. While its luminous structure is dramatic and visible across billions of light years, its very existence, its coherence, and its gravitational integrity suggests the presence of something invisible holding it all together, an enormous dark matter halo. In fact, Himiko's unexpected size, luminosity, and early formation make it one of the most tantalizing candidates for studying dark matter's role in the formative stages of galactic evolution. Dark matter, by its nature, does not interact with light. It does not emit, absorb, or reflect electromagnetic radiation, and thus cannot be observed using traditional telescopes. But we know it's there, because it interacts with gravity. Galaxies rotate in ways that cannot be explained by visible matter alone. Their outer stars orbit too fast for the amount of mass we can detect. The conclusion, supported by decades of evidence, is that galaxies are embedded in vast halos of unseen matter, spherical distributions of dark matter that extend well beyond their luminous regions. For a galaxy like Himiko to be so massive and organized so early, just 800 million years after the Big Bang, it must have formed in a region of space where dark matter had already collapsed into a significant gravitational well. This is no minor point. In the standard model of cosmology, structures form hierarchically. Small clumps of dark matter coalesce first, gradually merging to form larger halos, which then gather gas and eventually ignite star formation. The largest galaxies, in this view, should take time to grow. But Himiko challenges that timeline. It appears to have jumped ahead, rapidly accumulating mass and forming stars at a rate of roughly 100 solar masses per year. Such a leap demands a deeper explanation, and dark matter provides one. To sustain its size, some 55,000 light-years across, and to resist being torn apart by the violent turbulence of its environment, Himiko must be anchored by a dark matter halo of extraordinary mass. The visible matter, gas, stars, and radiation, is just the tip of the iceberg. The real mass of Himiko likely lies hidden in the invisible halo surrounding it, pulling matter inward, binding it gravitationally, and stabilizing its internal dynamics enough to allow rapid star formation to continue without the entire structure dissolving into chaos. Simulations of galaxy formation suggest that a galaxy as large and luminous as Himiko, especially at Z6.6, would require a dark matter halo with a mass of around 10 superscript 1 superscript 1 to 10 superscript 1 superscript 2 solar masses, comparable to the Milky Way's halo today. This is a staggering thought, that so early in the universe, a dark matter halo of such magnitude had already formed, gathered primordial gas, and enabled the creation of one of the most luminous galaxies of its epoch. If true, Himiko's halo is not just large, it's one of the earliest massive dark matter halos ever observed, a forerunner to the structures that now define the large-scale web of the cosmos. This insight is more than theoretical. The relationship between visible galaxy properties and the underlying dark matter halo is central to our understanding of cosmic structure. Himiko offers a unique opportunity to test this relationship in the early universe, to see if the laws that govern galaxy formation today were already in play during the universe's first billion years. Do high-mass halos always lead to high-luminosity galaxies? Did feedback from star formation or supernovae behave the same way in the early cosmos? Himiko may hold the answers. Moreover, the very geometry and morphology of Himiko hints at the role dark matter plays. The galaxy's three distinct clumps, likely representing merging substructures or intense starburst regions, could each be associated with subhalos of dark matter, smaller clumps nested within the larger gravitational structure. These subhalos may have coalesced rapidly, drawn together by the deeper gravity well of the main halo, a process consistent with the hierarchical assembly model of galaxy formation. Himiko, then, is not a smooth object, but a dark matter-fueled construction zone, with visible star formation tracing the intersections of invisible gravitational structures. There's another layer to this story. Dark matter halos also attract and retain gas, serving as reservoirs for star-forming material. In a young universe filled with hot, energetic particles, gravity needed a strong anchor to pull that gas in. Without a sufficiently deep potential well, without a dark matter halo, primordial hydrogen would have remained diffuse, resisting the collapse needed for star formation. Himiko's massive starburst activity implies that it not only pulled in gas, but held onto it, compressing it to densities high enough for new stars to form at staggering rates. This again points to the presence of a dominant dark matter component orchestrating the process. The study of dark matter halos is not just about explaining individual galaxies. It's also about understanding the cosmic scaffolding on which all structure is built. In modern cosmological simulations, dark matter forms a vast web, a lattice of filaments and nodes, on which galaxies form, grow, and evolve. The intersections of these filaments, called nodes, are where the most massive halos form. If Himiko is located at one of these nodes, and evidence suggests it might be, it's not just a galaxy, but a signpost of cosmic geography, a marker of where the universe was knitting itself together at the largest scales. Yet, we still haven't observed Himiko's dark matter directly. We infer its existence from gravitational effects, from its improbable luminosity, from the survival of its clumps, and from its star formation rates. But with future instruments, especially the James Webb Space Telescope and upcoming radio observatories like the Square Kilometre Array, we may gain better indirect measurements of its mass distribution, gas motion, and environment. These tools could help us map the halo, determine its shape and extent, and even identify satellite galaxies or inflowing streams of gas drawn in by gravity. In that sense, Himiko's dark matter halo is not just a supporting character, it is the silent architect of everything we see. It gathered the gas, sustained the starbursts, defined the structure, and allowed this rare cosmic beacon to emerge against all odds. Without it, Himiko would not exist. With it, we are gifted a glimpse not only into the light of the early universe, but into the shadowy forces that made that light possible. Though Himiko is not the very first galaxy to ever form, its incredible distance and early appearance in the cosmic timeline make it one of our best observational candidates for hosting population 3 stars, a theoretical generation of stars so ancient, so pristine, that they were forged directly from the primordial materials left over from the Big Bang. These stars are the ultimate goalpost for astronomers studying the origins of light and structure in the universe. And in Himiko's chaotic, ultra-young environment, surging with star formation and mostly devoid of heavier elements, there's a compelling case that traces of these elusive stellar pioneers might still flicker in its clumpy glow. To understand the importance of this possibility, we need to step back and look at the early universe's chemical composition. Right after the Big Bang, the universe was composed almost entirely of hydrogen and helium, with only trace amounts of lithium and virtually no heavier elements, no oxygen, carbon, nitrogen, iron, or anything else made in stellar cores. The very first stars, known as population 3 stars, would have been born in this elementally pure environment. Lacking metals, these stars were expected to form in ways very different from those of later generations. They may have been enormous, hundreds of times the mass of our Sun, and lived brief, violent lives, burning brightly and dying quickly, often in spectacular supernovae, or even collapsing directly into black holes. Because of their extreme brightness and short lifespans, population 3 stars would have burned out long ago. None are believed to exist today. But the hunt for their footprints in ancient galaxies remains one of the most important goals in observational cosmology. And that's where Himiko comes into the picture. Himiko exists at redshift c6.6, meaning it formed just a few 100 million years after the universe's first stars were born. This is right in the theoretical window where some population 3 stars might still have been forming, or at least where their immediate successors, population 2 stars, might be blending with the last fading embers of those first stellar giants. What makes Himiko especially compelling is its combination of extreme star formation, high luminosity, and extremely low metal content. This last factor is crucial. Astronomers have found that Himiko exhibits almost no signs of heavy elements, suggesting that its star-forming regions have not been significantly polluted by previous generations of stars. In cosmic terms, Himiko is chemically pristine. This chemical purity is one of the strongest indirect arguments in favor of population 3 stars. In galaxies that have undergone multiple generations of stellar recycling, you typically see strong emissions from oxygen, carbon, and other heavier elements. These are created inside stars and blown out into space by stellar winds and supernovae. But Himiko, despite its intense brightness and massive stellar nurseries, shows very weak, or even absent metal lines, a fact confirmed by deep spectroscopy using some of the most powerful instruments available. This lack of metallicity suggests we might be observing a galaxy caught just before or during its first major chemical enrichment phase. Furthermore, simulations of early galaxy formation show that population 3 stars would likely form in isolated pockets within larger protogalaxies. Himiko, with its 3 distinct clumps, may well represent such an environment. One of these clumps could plausibly host the remnants, or even the final generation, of population 3 stars before their explosive deaths began to seed their surroundings with heavier elements. In this sense, Himiko is not merely old, it is primordial, a transitional object bridging the gap between the dark ages and the first lights of a chemically complex universe. There's also the sheer energy output to consider. Himiko's intense Lyman-alpha radiation and its very high inferred star formation rate could, in part, be driven by stars that are hotter, larger, and more extreme than what we typically see in nearby galaxies. Population 3 stars are theorized to emit enormous amounts of ionizing ultraviolet radiation, due to their massive sizes and high surface temperatures. The immense Lyman-alpha glow of Himiko might be more than just a byproduct of normal stellar activity. It could be a signature of an early, intense wave of stellar ignition, perhaps involving stars more extreme than any still existing in the modern universe. Yet despite all these compelling hints, direct detection of population 3 stars remains beyond current observational capabilities. We cannot yet resolve individual stars in Himiko. It's simply too far away and too faint in angular size. But astronomers continue to build a case using the collective properties of galaxies like it. If we can identify consistent patterns, such as the absence of metals, unusually high star formation rates, and extreme Lyman-alpha emission, then we may be able to infer the presence of population 3 activity with greater confidence. And this is where the James Webb Space Telescope enters the story once again. With its infrared sensitivity and unprecedented resolution, JWST is poised to examine galaxies like Himiko in more detail than ever before. It will be able to detect faint emission lines that trace metallicity, probe the ionization state of gas, and even measure the temperature of star-forming regions. If Himiko or a similar galaxy shows a spectrum consistent with metal-free or nearly metal-free stellar populations, we might finally come closer to confirming the existence of population 3 stars, not by seeing them directly, but by observing their chemical fingerprints embedded in the light of their host galaxies. In this way, Himiko is more than a beacon from the past, it is a possible archive of the universe's first generation of stars. Whether or not it still contains population 3 stars, or simply reflects their legacy, it offers a rare glimpse into a time when the universe was just beginning to forge the building blocks of everything that would follow. In Himiko, we might be seeing the very moment when darkness gave way to light, and the most primitive stars lit the cosmic stage for the first time. And if even one population 3 star flickered inside that galaxy's chaotic heart, then Himiko becomes not just a distant galaxy, but a sacred monument to the dawn of creation itself. For all we've observed, modeled, and hypothesized about Himiko, some of the most fundamental questions remain unresolved. At its core, the mystery of Himiko is not just about what it is, but what it means. Is this immense, luminous structure a single, unusually massive galaxy, defying the cosmic odds with its early emergence? Or is it something more complex, a group of galaxies merging, in the process of becoming a larger structure? Or perhaps, and this is the most provocative possibility, it represents a transient phase of galactic evolution that we've never directly observed before, a brief but blazing chapter in the history of cosmic assembly that doesn't neatly fit into any current classification. The issue begins with its structure. Himiko presents 3 bright clumps, each radiating intense Lyman-alpha light, distributed across a region roughly 55,000 light-years in diameter. To a casual glance, one might assume these are just dense star-forming regions within a single, enormous galaxy. But the spatial separation between the clumps, along with differences in brightness and morphology, leaves open the possibility that these are 3 distinct galaxies, gravitationally bound and possibly in the throes of a colossal merger. If so, then what we're witnessing isn't a finished galaxy, but a galactic collision in progress. A rare and chaotic event where proto-galaxies are drawn together by mutual gravity, funneling gas into their cores and igniting ferocious bursts of star formation. This would explain the high luminosity, the clumpy appearance, and perhaps even the extended gas halos. They could be shockwaves or outflows caused by the violence of interaction. Such an interpretation places Himiko in the company of other observed merger systems, but with one key difference. This is happening at a time when the universe was less than 1 billion years old. If Himiko is a merger, then galaxy collisions were occurring far earlier and on a much grander scale than we once believed possible. But what if it's not a merger? What if those 3 clumps are part of a single galaxy's internal structure, like the arms of an irregular, unrefined spiral, or massive star-forming regions scattered through a still-settling disk? The early universe was chaotic, after all. Galaxies did not form in neat, symmetrical arrangements. Without the stabilizing influence of metals, supermassive black holes, or mature dark matter dynamics, it's possible that Himiko is simply what a young, monolithic galaxy looks like in its raw, unregulated form. This interpretation would imply that Himiko achieved a high degree of mass assembly and star formation internally, rather than through mergers. A notion that challenges the hierarchical model of galaxy formation, which posits that small structures came first and combined to form larger ones over time. There's also the chance that Himiko isn't neatly one or the other, that it's not a galaxy, in the conventional sense at all. It might be part of a protocluster, a dense region of space where galaxies are forming in close proximity, bound by gravity but not yet merged into a single object. These protoclusters are the seeds of today's galaxy clusters, and finding one at this redshift would be monumental. If Himiko is such a structure, we may be seeing the cosmic web in its earliest threads, a dense knot of matter coalescing into what will eventually become one of the most massive systems in the universe. This would also make Himiko a tracer of large-scale structure formation, offering clues about how filaments, nodes, and voids in the cosmic web began to take shape. Even more intriguingly, Himiko may represent a completely unknown evolutionary stage, a fleeting transitional period that galaxies pass through during their early development, but that is difficult to catch because it happens so quickly, and so long ago. Most of our galaxy classification systems, spirals, ellipticals, irregulars, are based on present-day observations. But the universe in its infancy likely hosted phases of galactic evolution that don't neatly align with these categories. Himiko, with its raw structure, extreme brightness, and rapid star formation, could be a missing link between the first gas clouds and the first mature galaxies. It might not be unusual at all, just underobserved, hiding in the dark corners of the early cosmos. One major challenge in settling these questions lies in our limited resolution at such great distances. Even with the Hubble and Spitzer telescopes, Himiko is barely resolved. Its structure, dynamics, and environment are blurred by distance, redshift, and cosmic interference. Only now, with instruments like the James Webb Space Telescope, do we have the sensitivity and clarity to start disentangling these possibilities. JWST may be able to resolve the 3 clumps, measure their velocities, detect subtle shifts in their light, and determine whether they are orbiting each other, merging, or simply part of a single structure. It may also detect fainter galaxies or streams of gas nearby, revealing whether Himiko sits alone or within a larger protogalactic complex. But even with JWST, Himiko poses a profound philosophical question to astronomers. How do we define a galaxy at the edge of time? Are our modern classifications and models even applicable to objects born under such different physical conditions? The early universe was a furnace of rapid change. The rules were different, the environments harsher, and the timelines compressed. Himiko may not just be an unusual galaxy, it may be a relic of a forgotten mode of cosmic construction, something that was common once, but faded quickly into the background as the universe matured. In the end, the beauty of Himiko lies not just in what we've discovered, but in what we still don't know. Its clumps, its light, its silence where metals should sing, all of it speaks to a cosmic enigma we've only just begun to understand. Himiko might be 3 galaxies or 1. It might be collapsing, colliding, or coalescing. It might be a flare of the first stars or a blueprint of the first clusters. It is one object, many questions, a mirror to our own evolving understanding of the universe. And perhaps that's the most compelling thing of all. Himiko doesn't just illuminate the early cosmos, it shines a light on the limits of our own knowledge, and the boundless horizon that still lies ahead. The James Webb Space Telescope, JWST, is not just the next chapter in space exploration, it's the most powerful time machine humanity has ever built. While telescopes like Hubble and Spitzer gave us glimpses of the distant universe, JWST offers a full, penetrating stare into the very dawn of galaxies like Himiko. And for an object as enigmatic and extreme as Himiko, Webb's unmatched sensitivity in the infrared is nothing short of transformative. This is the telescope that will finally peel back the cosmic veil surrounding Himiko, revealing the truths hidden in its light, structure, and history. JWST was specifically designed to observe the universe in the infrared, precisely the range of wavelengths into which Himiko's ancient light has been stretched by billions of years of cosmic expansion. While older telescopes struggled to resolve the fine details of galaxies at redshift Z6.6, JWST can cut through the noise, capturing clear, high-resolution images of galaxies from even earlier epochs. That means Himiko, already on the radar as a scientific mystery, is a prime target for this revolutionary observatory. One of the first questions JWST can help address is the true nature of Himiko's structure. Those 3 bright clumps we've observed, are they regions of intense star formation within a single, massive galaxy? Or are they individual galaxies still in the process of merging? Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, will allow scientists to map the galaxy's morphology with unprecedented clarity, revealing not just the shapes and edges of each clump but also their spatial distribution, internal turbulence, and perhaps even stellar population differences. This could answer the long-standing debate, is Himiko one galaxy, a merger, or something else entirely? Even more critically, JWST can probe the chemical composition of Himiko in far greater detail than any observatory before it. Its spectroscopic instruments, especially NIR-SPEC, near-infrared spectrograph, can dissect the light coming from different parts of the galaxy to reveal the presence, or absence, of various elements. This is vital because Himiko has so far shown very little evidence of heavy elements, hinting at an unusually pristine environment possibly hosting population 3 stars. With JWST, we may finally be able to quantify the metallicity of Himiko's gas and stars, confirming whether it's truly chemically primitive or simply less enriched than its peers. If Himiko does turn out to contain stars with 0 or near-zero metallicity, that would be monumental. It would mark the first indirect evidence of population 3 stars, those hypothetical giants formed from the primordial hydrogen and helium of the early universe. The telescope may detect specific emission lines that are characteristic of metal-free stellar populations or trace the ionization state of the gas to determine whether the energy being pumped into the surrounding halo could realistically come from such stars. Even a single hint of this could reshape our understanding of stellar evolution's earliest chapter. Beyond stellar populations, JWST can map Himiko's gas dynamics, how matter moves inside and around the galaxy. By analyzing the shifts in emission lines like Lyman-alpha and H-alpha, JWST will be able to determine whether gas is flowing inward, collapsing into new stars, or being blasted out by winds from supernovae or nascent black holes. This would help solve another riddle. How can Himiko sustain such intense star formation without showing signs of the feedback mechanisms, like supernova-driven winds, that usually slow down or regulate galactic growth? If the gas is unusually dense or shielded, or if feedback is delayed or suppressed in some way, JWST might be the first to detect that phenomenon directly. There's also the possibility that Himiko contains hidden companions, smaller satellite galaxies or inflowing streams of material that have gone undetected by earlier telescopes. JWST's deep field sensitivity could uncover these structures, revealing whether Himiko is growing in isolation or embedded in a larger web of forming galaxies. This could settle the debate about whether it's a one-off anomaly or part of a greater protocluster, a crucial piece of the puzzle when it comes to understanding how large-scale structure emerged in the early universe. Another essential JWST capability is in observing dust and molecular gas. Himiko appears to be surprisingly dust-free, given its intense star formation. With JWST, astronomers can search for the thermal signatures of warm dust, even in trace amounts. Its mid-infrared capabilities make it uniquely suited to detect molecules like carbon monoxide or water, which are often present in star-forming regions. If Himiko lacks these completely, that would confirm just how pristine it truly is. But if small amounts are detected, we may be witnessing the very first stages of chemical enrichment, where dust is only beginning to form from the earliest supernovae. And finally, JWST has the power to look beyond Himiko, not just at the galaxy itself, but at the intergalactic medium surrounding it. This is essential for studying the state of the universe during the Epoch of Reionization, when Himiko existed. By analyzing how the galaxy's light is absorbed or scattered on its way to us, JWST can map the distribution of neutral hydrogen in the area. Is Himiko in a fully reionized bubble, or is it fighting to carve one out on its own? Are there signs of a larger reionization front moving across the sky? Himiko's brightness makes it the perfect probe for this question, and JWST could finally confirm its role as both a witness and an agent of cosmic reionization. In essence, JWST won't just study Himiko. It will interrogate it, peeling back each layer of complexity, forcing it to reveal the secrets it has held since the cosmic dawn. This telescope is more than just a tool. It's a translator between now and then, between theory and evidence, between wonder and understanding. What Himiko has shown us so far has already rewritten parts of the cosmic story. But what it's about to reveal, through the eye of the most powerful observatory ever built, may challenge our assumptions even further. In the silent light that has traveled for over 12.9 billion years, answers await. JWST is now listening. In the end, Himiko is more than just a galaxy. It's a cosmic message in a bottle, cast across the vast ocean of time. Its light, ancient and unyielding, has traversed nearly 13 billion years to reach us, whispering secrets from an era before the universe had even begun to settle. It flickered to life during a time when darkness still reigned, when stars were just beginning to carve paths through the fog of neutral hydrogen, and yet it blazed so brightly that it continues to dazzle modern telescopes. Himiko is a reminder that even in the deepest obscurity, something extraordinary was already taking shape. Light was not only surviving, it was rising, fierce, fast, and full of mysteries. In that glow, we see the ambitions of nature played out on a colossal scale. A galaxy so large, so luminous, and so complex, at a time when most galaxies were still gas clouds, is more than just a scientific anomaly. It's a challenge. It demands that we re-examine our models, our equations, and our expectations. Himiko tells us that the early universe was not just a gradual rise out of simplicity but a cauldron of extremes, where massive structures could form quickly, where the rules were flexible, and where something like Himiko could exist against all odds. It is humbling to realize that when Himiko first lit the sky, our own sun would not exist for another 8 billion years. Earth had not formed, life had not stirred, and yet this galaxy had already lived, flared, and perhaps even begun to fade. In its light, we're not just seeing a scientific artifact, we're peering into a reality so distant, so alien, that it almost becomes mythological. And yet it is real. It existed. And it reached out across time to find us. Through Himiko, we glimpsed the first acts of galactic theater, the early explosions of creativity that shaped everything that followed. Every spiral arm in the modern universe, every planet, every star, every atom forged in a supernova, they all have their roots in these early galaxies. Himiko is a fossil, yes, but not a cold one. It is a living ember, still burning in our telescopes, still shaping the questions we ask, still teaching us how our universe came to be. And what makes it even more profound is this: we almost missed it. Without the sensitivity of modern telescopes, without the curiosity to look deeper, Himiko might have remained hidden forever, its story untold, its light absorbed into the silence of deep space. That we found it at all speaks to the power of human exploration, and to the endless possibilities waiting in the shadows of the unknown. There will be more discoveries. The James Webb Space Telescope and other future missions will find galaxies like Himiko, and perhaps even stranger. We will uncover more of the early universe, rewrite more of our textbooks, and peel back more layers of cosmic time. But Himiko will always be one of the first beacons that told us we had barely scratched the surface. Because in the ancient glow of Himiko, we are reminded that even when the universe was young, it was already bold, already fierce, already filled with brilliance no theory could predict. And that in the darkest ages, light was not waiting, it was racing ahead. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.